Right now, at this very moment, you are looking at the past. Every star you see in the night sky is already gone, or at least the version of it you are seeing no longer exists. The light reaching your eyes left those stars years ago, decades ago, centuries ago. Some of them thousands of years before you were born. You are not looking at the universe as it is. You are looking at its memory. And here is what keeps me awake at night, or perhaps what should help you fall asleep. If light from distant stars takes so long to reach us, then what we call the present moment is really just a collection of different pasts, all arriving at different times, all pretending to exist together in what we call now. Time itself is not what we think it is. The universe does not move forward in neat little seconds like the clock on your wall. It bends, it stretches, it remembers. Tonight, I want to take you on a journey through the cosmos, not the loud, explosive universe you see in movies, but the real one, the quiet one, the patient one, the one that has been unfolding for nearly 14 billion years and will continue long after every human memory fades into dust. We are going to float through the silence of space, where sound does not exist because there is nothing for it to travel through. We are going to visit dying stars that take longer to fade than our entire planet has existed. We are going to discover that you, yes, you lying in your bed right now, are made from the remains of ancient suns that exploded before Earth was even a thought in the universe's mind. But there is something else, something the universe has been hiding from us, something about the nature of time and light and existence that will make you question whether anything is truly real, or if we are all just echoes of something that happened long ago, still rippling through the fabric of space. And that answer waits for us, out there in the dark, between the stars. Hey guys, tonight we begin with the vast, silent universe and its most peaceful mysteries, the cosmic wonders that have existed for billions of years, waiting patiently in the endless dark, from the gentle drift of stardust to the slow dance of galaxies spinning through space. Their story is one of time, beauty, and infinite patience. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you are tuning in from and what time it is for you. It is always fascinating to see who is joining us from around the world. Now dim the lights, maybe turn on a fan for that soft background hum. Get into your blanket and let us ease into tonight's journey together. Let us begin with a simple fact that will change how you see the night sky forever. Light travels at exactly 186,282 miles per second, not approximately, not roughly, exactly that speed. It is one of the few constants in our universe, something we can rely on, something that never changes no matter where you are or how fast you are moving. Light always travels at the same speed through the vacuum of space. Always. But here is what that means for us, lying on our tiny planet, looking up at the stars. The nearest star to Earth, besides our Sun, is called Proxima Centauri. It sits about 4.2 light years away from us. That means the light we see from that star tonight left its surface 4 years and 2 months ago. When you look at Proxima Centauri, you are not seeing it as it is right now. You are seeing it as it was in the spring of 2021. You are looking at a star that might not even exist anymore, and you would not know for another 4 years. Now let us go farther. Sirius, the brightest star in our night sky, is 8.6 light years away. The light you see from Sirius left that star when you were 8 years younger than you are now, or if you are younger than 8, it left before you were born. Betelgeuse, that reddish star in the constellation Orion, is about 700 light years away. The light from Betelgeuse that reaches your eyes tonight began its journey during the year 1325, when the Aztec Empire was just beginning to rise and the Renaissance had not yet touched Europe. Every time you look up, you are looking at history. The night sky is not a snapshot of the present, it is a museum of time, each star showing you a different moment from the past, all scattered across the centuries. But we can go even farther, so much farther. The Andromeda Galaxy, our nearest large galactic neighbor, floats 2.5 million light years away from us. When you see that faint smudge of light in the autumn sky, you are seeing Andromeda as it appeared 2.5 million years ago. That light began its journey to Earth when our ancestors were still Australopithecus, barely walking upright, using simple stone tools, with brains half the size of ours. Everything you see in Andromeda, every star in that spiral galaxy, is showing you a version of itself from a time when humans did not exist. Think about that for a moment. The light traveling from Andromeda to your eyes right now has been moving through empty space for 2.5 million years. It passed through clouds of dust. It bent around gravitational fields. It just kept going, moving at 186,282 miles per second, never stopping, never slowing, for longer than our species has walked this earth. And tonight, after all that time, all that distance, it finally arrived at your eye. You caught it. You saw a moment from the deep past. This is what I mean when I say the universe is patient. There is no rush in space. Light does not hurry. Stars do not panic. Everything moves at its own eternal pace, following the laws of physics with perfect consistency. A photon of light leaves a distant star and begins its journey across the cosmos. It does not know where it is going. It does not know if anyone will see it. It just travels for years, for centuries, for millions of years, until perhaps, just maybe, it reaches a planet where someone is lying in bed, looking up, wondering about the universe. And here is the beautiful part. Here is the part that makes me feel calm, even in the chaos of daily life. The universe is not happening all at once. The present moment we experience is just a thin slice of reality, a narrow window where different light from different times happens to arrive at the same instant. When you look at the night sky, you are seeing 1,000 different moments in history, all layered on top of each other. Some stars are showing you last week. Some are showing you the Middle Ages. Some are showing you a time before humans existed. Time, as we experience it, is just a local phenomenon. It only feels linear because we are trapped inside it, moving forward at 1 second per second. But the universe does not experience time the way we do. Out there in the vast dark between the stars, time stretches, it bends, it plays tricks. And this brings us to something even stranger. If you could somehow travel faster than light, which physics says you cannot, but if you could, you would arrive at a distant star before the light from Earth reached it. You would see Earth as it was in the past. You could watch history play out in reverse, watching light from different centuries arrive in backwards order. You could see the pyramids being built, then unbuilt. You could watch the dinosaurs roam, then disappear, all because light, despite its incredible speed, is still slow compared to the distances of space. The universe has a speed limit, and because of that speed limit, the past is always with us. It surrounds us. Every direction we look, we are looking backwards through time. The farther we look, the farther back we see. Some of the most distant galaxies ever observed are so far away that their light has been traveling for over 13 billion years. Those galaxies appear to us as they were when the universe was only 700 million years old, just a baby, still forming its first stars. Those galaxies might not exist anymore. They might have collided with other galaxies billions of years ago. They might be completely different now, but we will not know for billions more years because that is how long it will take for the new light to reach us. This is the cosmic waiting game. This is the universe teaching us patience. Right now, light is leaving Earth and traveling into space. In 8 minutes, it will reach Mars. In 40 minutes, it will pass Jupiter. In 5 hours, it will clear Pluto and enter the Kuiper Belt. In 4 years, it will reach Proxima Centauri. In 2.5 million years, it will finally arrive at Andromeda Galaxy. And maybe, just maybe, someone there will look up at their night sky, see a faint yellow star, and wonder if anyone is looking back. But they will not be seeing us as we are now. They will be seeing us as we were 2.5 million years ago. They will be seeing Earth in its ice age, watching glaciers cover the northern continents, watching our ancestors hunt mammoths with stone spears. They will see our past while living in what, to them, is the present. And when they send light back to us, we will not see them as they are in that moment either. We will see them as they were another 2.5 million years before. By the time their light reaches us, 5 million years will have passed. We could be gone by then. Our entire species could be extinct, and the light carrying news of Andromeda's response would arrive at an empty planet, with no one left to see it. This is the loneliness of space. This is the price of distance. Everything is delayed. Everything takes time. The universe does not allow for instant communication. It demands patience. It insists on waiting. And yet, there is something beautiful about this, something calming. We are not meant to know everything instantly. We are not supposed to see the universe as it truly is in this exact moment. We are meant to see it the way it was, layer by layer, light by light, memory by memory. We are meant to look up at the night sky and see history written in starlight. We are meant to feel small but connected, part of something so vast and so old that our individual worries, our daily stress, our anxieties about tomorrow all fade away into insignificance. Because out there, right now, light is traveling. Photons are crossing the emptiness between stars, carrying information, carrying images, carrying the past into the future. They have been traveling for longer than you have been alive. They will continue traveling long after you are gone. And that is okay. That is the way the universe works, patiently, eternally, without rush. So tonight, as you begin to drift off to sleep, remember this: you are not watching the stars as they are, you are watching their memories. You are seeing ancient light from ancient times, all arriving at this moment just for you. The universe kept that light safe for centuries, for millennia, just so it could reach your eyes tonight. And tomorrow night, new light will arrive, light that has been traveling for just as long, showing you a slightly different version of the past. The stars will still be there, patiently shining, waiting for their light to cross the cosmic ocean and reach another pair of eyes. The universe has time, infinite, patient time, and so do you. Rest now. The stars will wait. There is a common misconception about the universe that I want to correct right now, tonight, before you fall asleep with the wrong image in your mind. Most people think stars die in violent explosions. They imagine supernovae, massive blasts that tear across space, destroying everything in their path. And yes, some stars do die that way, but those are the rare ones. Those are the exceptions. The truth about stellar death is far more gentle, far more patient, far more beautiful than anyone tells you. Most stars die quietly. They fade slowly over billions of years, cooling from white to yellow to orange to red, then finally to darkness. No explosion, no dramatic finale, just a long, peaceful dimming, like a candle burning down in an empty room. And honestly, that feels more appropriate somehow, more honest, because the universe is not dramatic. It does not need theatrics. It simply does what it has always done, which is exist, change, and continue. Let me tell you about our sun first, because its death is already written. Scientists know exactly how it will happen. They have calculated it down to the million-year mark. Right now, our sun is middle aged. It has been burning for about 4.6 billion years, fusing hydrogen into helium in its core, releasing energy that travels 93 million miles to warm our planet and make life possible. But that process cannot last forever. Eventually, about 5 billion years from now, the hydrogen fuel in the sun's core will run out. And when that happens, something beautiful will occur. The core will start to collapse under its own gravity. As it collapses, it will heat up, and that heat will cause the outer layers of the sun to expand. Slowly, over millions of years, our sun will swell. It will grow larger and larger, its surface cooling as it stretches outward. The yellow star we know will turn orange, then red. It will become what astronomers call a red giant. At its largest, the sun will expand beyond the orbit of Mercury. It will swallow Venus entirely. Earth might survive at the outer edge, but barely. The oceans will boil away. The atmosphere will strip off into space. Our planet will become a scorched, lifeless rock orbiting inside the outer layers of our dying star. But this will not happen quickly. This transformation takes tens of millions of years. The sun will not suddenly explode. It will just slowly grow, slowly cool, and slowly change. And here is what gets me. Here is the part that makes me stop and think. 5 billion years is longer than Earth has existed. 5 billion years ago, our planet was just forming from dust and gas. 5 billion years ago, there were no oceans, no continents, no life. Everything we know, everything that has ever lived, every human who has ever existed, all of recorded history, all of evolution, all of it fits inside a period shorter than the time our sun has left. We are living in the middle of our star's life, not at the beginning, but not at the end either. We exist during its golden age, when it burns steady and yellow and perfect for life. Someday that age will end, but not today, not for 5 billion tomorrows. When the sun finally becomes a red giant, its core will continue collapsing until it gets hot enough to fuse helium into carbon and oxygen. For a brief time, maybe 100 million years, the sun will stabilize again. It will burn helium instead of hydrogen, but eventually that fuel will run out too. And when it does, the sun will not have enough mass to fuse anything heavier. It will not go supernova. It will not explode. It will simply run out of options. The outer layers will gently puff away into space, forming what astronomers call a planetary nebula, not because it has anything to do with planets, but because early astronomers thought these objects looked like planets through their telescopes. A planetary nebula is just the outer shell of a dying star, drifting slowly outward, glowing softly from the heat of the core it left behind. And at the center, where the sun used to be, there will be a small, dense object about the size of Earth, a white dwarf, the compressed core of our former star, incredibly hot, incredibly dense, made mostly of carbon and oxygen. It will shine brightly at first, not from fusion, but just from leftover heat, and then over trillions of years, it will cool slowly, patiently, until it becomes a black dwarf, a cold, dark cinder floating through space, no longer giving off any light at all. That is how most stars die. Not with a bang, but with a fade. About 97% of all stars in the universe will end this way, quietly, peacefully, turning into white dwarfs and eventually black dwarfs. The dramatic supernovae you see in documentaries only happen to the most massive stars, the ones many times heavier than our sun. Those are the rare cases, the outliers. Most stars simply burn through their fuel and gently release their outer layers into space. And that process, that slow release of stellar material, is not destruction, it is transformation. When a star becomes a planetary nebula, it spreads its atoms across space: carbon, nitrogen, oxygen, all the elements created inside the star's core during billions of years of fusion. Those atoms drift through the interstellar medium, mixing with hydrogen and helium left over from the Big Bang. Eventually, they join clouds of gas and dust that will collapse to form new stars, new planets, new worlds. Nothing is wasted in the universe. Everything is recycled. Every atom that was once inside a star will become part of something else, maybe another star, maybe a planet, maybe billions of years from now, a living creature on some distant world, looking up at the sky and wondering where it came from. This is the circle of stellar life: birth, fusion, death, rebirth, over and over, for billions of years, across trillions of stars. The universe does not mourn its dying stars, because it knows they will return in a different form. Let me tell you about one of the most beautiful objects we have ever observed, the Helix Nebula, also called the Eye of God, though I prefer its official name because it sounds less dramatic and more honest. The Helix Nebula is a planetary nebula about 650 light years away from Earth. It is what remains of a star that died thousands of years ago. When you look at images of the Helix Nebula, you see a ring of glowing gas, delicate shades of red and blue and green, expanding slowly into space. At the center, a white dwarf, small and hot, lighting up the gas around it like a lamp inside a paper lantern. The whole structure is about 2.5 light years across and still growing, still spreading outward at about 20 miles per second. But from our perspective, 650 light years away, it looks frozen. It looks eternal, a cosmic flower blooming in the dark. That star died peacefully. It did not explode, it just let go. And someday, maybe 4 or 5 billion years from now, when our sun reaches the end of its life, it will create something similar, a glowing shell of gas, drifting outward, lit from within by the white dwarf core. Future beings, if any exist, will look at it from distant planets and see it as beautiful. They will not see it as an ending. They will see it as art, as nature's way of painting with light and gas and time. Now let us talk about the stars that do explode, because even though they are rare, they play an important role in the universe's story. Only stars with at least 8 times the mass of our Sun can go supernova. These massive stars burn through their fuel much faster than smaller stars. While our Sun will last 10 billion years, a star 20 times more massive might only last 10 million years. They live fast, they die young, and when they die spectacularly. Inside a massive star's core, fusion continues far beyond helium. The star fuses carbon into neon, neon into oxygen, oxygen into silicon, silicon into iron. Each stage of fusion releases less energy than the last. Each stage happens faster. Hydrogen fusion might last millions of years. Iron fusion lasts less than a day. And then the star hits a wall. Iron. Iron does not release energy when it fuses. It absorbs energy. So when the core fills with iron, fusion stops completely. The core, no longer supported by the outward pressure of fusion, collapses in less than a second. The core temperature spikes to billions of degrees. Protons and electrons smash together, forming neutrons. The entire core becomes a ball of neutrons, compressed to unimaginable density. A teaspoon of this material would weigh as much as Mount Everest. And then the collapse stops. Suddenly, the core becomes so dense that even gravity cannot compress it further. It rebounds. That rebound sends a shock wave outward through the star's outer layers, ripping them apart and blasting them into space at 10% the speed of light. The explosion is so bright that for a few weeks, a single supernova can outshine an entire galaxy containing hundreds of billions of stars. That is the dramatic death. That is the one you see in movies. But even this violence serves a purpose. Supernovae create elements heavier than iron, gold, silver, platinum, uranium. These elements only form during the incredible heat and pressure of a supernova explosion. Every gold ring ever made, every silver coin, every piece of platinum in a catalytic converter, all of it came from supernovae that exploded billions of years ago. The explosion scattered those atoms across space, where they eventually became part of the gas clouds that formed our solar system. So, yes, some stars die violently, but even that violence is creative. Even that destruction builds something new. Most of the time, though, the universe prefers the quiet approach, the slow fade, the gentle release. Stars do not need to explode to matter. They can simply shine for billions of years, then dim, then darken, and that is enough. Right now, there are red giants scattered throughout our galaxy, old stars in their final stages, swollen and cool, glowing softly in the infrared. Betelgeuse, that star I mentioned earlier, is probably one of them. It has already left the main sequence. It has already started dying. Astronomers think it might go supernova sometime in the next 100,000 years, maybe sooner, maybe later. We do not know exactly when, but when it does, when that star finally explodes, we will see it from Earth. Even though Betelgeuse is 700 light years away, the supernova will be bright enough to see during the day. For a few weeks, we will have two suns in the sky, and then Betelgeuse will fade, leaving behind a neutron star or maybe a black hole, and the night sky will be forever changed. But until then, Betelgeuse just keeps shining, keeps glowing, keeps existing, because that is what stars do. They shine until they cannot anymore, and then they let go. There is something deeply calming about that, something that helps me sleep at night. The universe does not cling, it does not hold on desperately to what it has. Stars burn for as long as they can, and when their fuel runs out, they accept it. They transform. They become something else. They do not fight the inevitable. They do not panic. They just continue existing in whatever form comes next. White dwarfs can last for trillions of years, far longer than the current age of the universe. No white dwarf has ever cooled completely into a black dwarf, yet because the universe is not old enough. But eventually, given enough time, they all will. They will all fade to black, and that is okay. That is part of the process. Everything that begins must eventually end. Everything that shines must eventually dim. But the atoms remain. The energy remains. Transformed, scattered, mixed with other atoms, other energy, waiting to become part of something new. Nothing truly dies in the universe. It just changes shape. And that brings us to the next part of our journey, the part where we discover what happens to all that stellar material after the stars release it. Where does it go? What does it become? The answer might surprise you. Actually, the answer is you. You are what happens to dead stars. You are where their atoms went, and I am going to show you exactly how that works. But for now, rest easy knowing that even the stars are mortal. Even the brightest lights in the sky will eventually fade, and there is peace in that. There is acceptance. The universe teaches us that endings are not failures. They are just transitions, just another step in an endless cycle of creation and transformation. The stars are dying. They have been dying since the universe began, and they will continue dying long after we are gone. But their light still reaches us, their atoms still surround us, and tomorrow night, when you look up at the sky, you will see both the living and the dead all shining together, all part of the same eternal dance. I need you to understand something that will change how you see yourself, how you see other people, how you see everything around you. You are not separate from the universe. You are not an observer looking at space from the outside. You are space. You are the universe experiencing itself. Every atom in your body, except for hydrogen, was created inside the core of a dying star billions of years ago. You are not made of earth. You are made of stars. Let me prove it to you. The Big Bang happened 13.8 billion years ago. In the first 3 minutes after the universe began, only the simplest elements formed: hydrogen, helium, and tiny traces of lithium. That was it. The early universe was just a hot soup of these three elements, slowly cooling, slowly spreading out, waiting for something to happen. And for hundreds of millions of years, nothing did. The universe was dark. No stars, no planets, no light except the fading glow of the Big Bang itself. Then gravity began to pull the hydrogen and helium together, clouds of gas collapsed under their own weight. They heated up, they compressed, and eventually they became dense enough and hot enough for hydrogen atoms to fuse into helium. The first stars ignited. These were not stars like our sun. They were monsters, some of them hundreds of times more massive than any star alive today. They burned incredibly hot and died incredibly fast, maybe only a few million years after forming, and when they died, they exploded as supernovae, scattering the first heavy elements across the universe: carbon, oxygen, nitrogen, silicon, iron, all created inside those massive first generation stars. Those atoms drifted through space and mixed with the remaining hydrogen and helium. New stars formed from that enriched gas. Those stars created even more heavy elements. They died and released their atoms. More stars formed, more elements spread. Generation after generation of stars, each one adding to the chemical diversity of the universe. Thor's sun is a third generation star, maybe fourth. We are not sure exactly, but we know it formed from a cloud of gas that already contained heavy elements from previous stellar generations. That cloud collapsed about 4.6 billion years ago. Most of the material became the sun, but about 1% of it formed a disk around the young star, and from that disk, planets condensed, including Earth, which means Earth is made of stardust. The iron core at the center of our planet came from ancient supernovae. The silicon in the rocks came from dying stars. The oxygen in the atmosphere came from stellar fusion. Everything solid you have ever touched was forged inside a star. But here is where it gets personal. The human body is made of about 65% oxygen, 18% carbon, 10% hydrogen, 3% nitrogen, and small amounts of calcium, phosphorus, potassium, sulfur, sodium, and trace elements like iron, zinc, and copper. Let us talk about where each of these came from. The hydrogen in your body is the only element that dates back to the Big Bang. Every hydrogen atom in your body is 13.8 billion years old. When you drink water, you are drinking hydrogen that has existed since the universe was 3 minutes old. Those hydrogen atoms have been part of countless molecules, countless stars, countless planets. They have been recycled through the cosmos for almost 14 billion years, and now, briefly, they are part of you. But everything else came from stars. The carbon in your body makes up about 18% of your mass. That is roughly 16 kilograms of carbon in an average adult. Every single carbon atom was created inside a star through helium fusion. 3 helium nuclei smash together to form one carbon nucleus. This process, called the triple alpha process, happens inside red giants. The carbon builds up in the star's core until the star dies and releases it into space. That carbon then becomes part of gas clouds, which become part of planets, which become part of living things. The carbon in your bones, your muscles, your DNA, all of it came from red giants that died billions of years ago. Oxygen makes up 65% of your body mass, about 43 kilograms in an average person. Oxygen forms inside massive stars through carbon fusion. As the star ages, it fuses carbon into oxygen into silicon, building heavier and heavier elements. When the star finally explodes as a supernova, it releases all that oxygen into space. The oxygen you breathe right now, the oxygen in your blood, The oxygen in every cell of your body came from supernova. Nitrogen, which makes up 3% of your body, is created through a process called the CNO cycle inside stars. Carbon, nitrogen, and oxygen cycle through fusion reactions, each one briefly becoming the other, releasing energy in the process. Nitrogen is part of every amino acid, every protein, every strand of DNA in your body. Without nitrogen, life would not exist, and nitrogen only exists because stars created it. Calcium, which makes up about 1.5% of your body and gives strength to your bones and teeth, also comes from supernovae. When massive stars explode, the intense heat and pressure create calcium nuclei. That calcium eventually becomes part of planets, and eventually part of you. Phosphorus, essential for DNA and ATP, the molecule that powers every cell in your body, comes from supernovae. Iron, which carries oxygen in your blood, comes from the cores of massive stars. Every time your heart beats, iron atoms forged inside a dying star billions of years ago carry oxygen to your cells. Every thought you think requires calcium ions created in a supernova explosion. Every movement you make is powered by phosphorus from stellar nucleosynthesis. You are not just made of stardust. You are a walking collection of atoms that have existed for billions of years, that have been through multiple stars, multiple planets, multiple forms. The atoms in your left hand might have come from a different star than the atoms in your right hand. The calcium in your bones might be older than the iron in your blood. You are a mixture of stellar remnants, all temporarily organized into the pattern we call a human being. And here is the part that always gets me. Here is the part that makes me stop and think. Those atoms will not stay with you forever. You are borrowing them. In a few decades, your body will break down and those atoms will return to Earth. They will become part of the soil, part of plants, part of other animals, part of the air. Maybe some of them will become part of another person. Maybe some will stay in the ground for millions of years. Maybe some will eventually escape Earth's gravity and drift back into space, waiting to become part of another planet, another star, another cycle of creation. Nothing in the universe is permanent. Everything is just temporarily organized. You are a pattern that atoms happen to form for a brief moment in cosmic time, and then those atoms will form other patterns, other beings, the other things. The universe does not hold on, it lets go, it transforms. Every person you have ever met is made of stardust. Every tree, every animal, every insect, every blade of grass, all of it came from stars. The ground beneath your feet is stardust. The water you drink is stardust, mixed with ancient hydrogen. We are all connected through this shared origin, the shared history, written in the elements themselves. Carl Sagan said it best. We are a way for the cosmos to know itself. We are the universe looking at itself, thinking about itself, trying to understand itself. The atoms in your brain were created in stellar cores billions of years ago. Those atoms have traveled across light years of space, through clouds of gas and dust, through the formation of the solar system, through billions of years of Earth's history, through the evolution of life, all to become part of you. And now those atoms are arranged in such a way that they can wonder about their own origins. They can look up at the night sky and recognize their birthplace. That is not poetic exaggeration. That is literal truth. You are made of stars. Your body contains the remnants of stellar explosions. Your very existence is proof that stars die and create new things. You are the answer to the question of what happens after a star dies. This is what happens. Life happens. Consciousness happens. Wonder happens. Scientists estimate that about 40,000 tons of cosmic dust falls on Earth every year. That dust is made of tiny particles, remnants of ancient stars, slowly drifting through space until they encounter our atmosphere and settle on the surface, which means every year Earth gains 40,000 tons of stardust. Some of that dust lands in the ocean and dissolves into the water. Some lands on soil and becomes part of the ground. Some is breathed in by living things. The process never stops. We are constantly being dusted with stellar material. And it goes the other way too. Earth loses about 3 kilograms of hydrogen per second to space. The lightest atoms in our atmosphere can reach high enough speeds to escape gravity entirely. They drift away and join the solar wind, eventually spreading through interstellar space. So Earth is slowly losing its hydrogen, atom by atom, while simultaneously gaining heavier elements from cosmic dust. The planet is exchanging material with the universe constantly, always in flux, always transforming. You are part of that exchange. The atoms you are made of came from space and will return to space. You are temporary, but the atoms are forever. They will outlast you by billions of years. They existed before you were born and will exist long after you die. They do not care about your name or your memories or your achievements. They are just atoms following the laws of physics, participating in the endless cycle of stellar death and rebirth. And yet, for this brief moment, those atoms are arranged in a way that allows them to care, to think, to feel, to wonder. You are the universe's way of caring about itself. You are atoms that learn to love other atoms. You are stardust that learn to contemplate stardust. There is something deeply humbling and deeply beautiful about that. When you look at another person, you are looking at a different collection of stellar remnants, organized into a different pattern, but made of the same ancient material. We are all siblings in that sense, all children of the same cosmic nursery, all built from the same stellar Lego blocks. And when you think about it that way, a lot of human concerns start to feel small. The divisions we create between people, the borders, the categories, the hierarchies, all of it seems silly when you remember that we are all just temporary patterns made of ancient star material. We are all the same stuff, briefly aware of itself, trying to make sense of a universe that created us by accident. The universe did not plan for you to exist. Stars did not die specifically so you could be born. It all just happened through the natural unfolding of physical laws. Gravity pulled gas clouds together. Fusion created heavy elements. Stars died and scattered their atoms. Planets formed. Life evolved. And eventually, here you are, lying in bed, listening to someone tell you that you are made of stars. But even though it was not planned, even though it was all just physics and chemistry and random chance, it still happened. You exist. Against enormous odds, the atoms that make up your body found each other and organized themselves into something that can think and feel and wonder. That is remarkable. That is worth appreciating. So tonight, as you drift off to sleep, remember what you are made of. Remember that your body is a temporary home for atoms that have traveled across billions of years and trillions of miles to be here. Remember that you are stardust, given shape and breath and consciousness for a brief moment in cosmic time. And remember that when you look up at the stars, you are not looking at something foreign. You are looking at family. You are looking at the furnaces that created you. You are looking at home. The atoms in your body will outlast you. They will return to the universe when you are gone, and maybe, billions of years from now, they will become part of another star, another planet, another being. Maybe your atoms will travel to another galaxy. Maybe they will witness the end of the universe itself. But right now, in this moment, those atoms are you, and that is enough. That is more than enough. You are the universe experiencing itself. You are stardust that learned to dream. Rest now. The atoms will take care of the rest. Now that you know you are made of stardust, I need to tell you something that might surprise you, something that makes the universe even stranger than you imagine. Almost all of you is empty space. Not metaphorically, not philosophically, literally. The atoms that make up your body are 99.9999999999999999999999999999999999999999999999999999999. If you could remove all the empty space from all the atoms in your body, if you could compress all your protons, neutrons, and electrons into a solid mass with no gaps, you would be smaller than a grain of salt. Actually, smaller than that. You would be nearly invisible. All of humanity, every person who has ever lived, compressed down to pure matter, with no space between the particles, would fit inside a sugar cube. Think about that for a moment. You feel solid. You feel real. You can touch things, hold things, move through the world as a physical being, but you are mostly nothing. You are mostly the absence of matter. The feeling of solidity is an illusion created by electromagnetic forces between atoms, by electrons that refuse to occupy the same space. But the atoms themselves are almost entirely empty. And if that is true for your body, it is even more true for the universe. Space is not called space because we ran out of words. It is called space because that is what it mostly is. Empty space. Vast, cold, silent emptiness stretching between points of matter. The universe is the biggest empty room that has ever existed, decorated here and there with tiny specks of matter we call stars and planets and galaxies. Let me give you some numbers so you can understand the scale. The average density of the universe is about 1 hydrogen atom per cubic meter. That is it. One single atom in a space the size of a large refrigerator, and that is the average, which means most places have even less than that. The space between galaxies might have only 1 atom per 10 cubic meters, or 1 per 100 cubic meters. In some vast voids between galaxy clusters, you might travel for millions of miles without encountering a single particle. Compare that to air. The air you breathe contains about 25 quintillion molecules per cubic centimeter. That is 25 with 18 zeros after it. Every breath you take pulls in more atoms than there are stars in the observable universe. Air seems thin to us, almost like nothing, but compared to the vacuum of space, air is incredibly, impossibly dense. Even inside the solar system, where matter is relatively concentrated, space is still mostly empty. The distance from Earth to the moon is 238,855 miles. In all that space, there is almost nothing, a few hydrogen atoms per cubic centimeter in the solar wind, maybe some dust particles here and there, but mostly just emptiness. Light can travel that distance in 1.3 seconds because there is nothing to slow it down, nothing in the way. The distance from Earth to the Sun is 93 million miles. We call this an astronomical unit, and astronomers use it as a measuring stick for the solar system. Mars is 1.5 AU from the Sun. Jupiter is 5.2 AU. Neptune is 30 AU, and in all that space between the planets, there is almost nothing, just the thin solar wind, a stream of particles flowing out from the sun, and occasional comets passing through. But the vast majority of the space is empty. Voyager 1, the most distant human made object, has been traveling away from Earth since 1977. It is currently about 14.5 billion miles from home, moving at roughly 38,000 miles per hour. That sounds fast. That is faster than any human has ever traveled. But at that speed, Voyager 1 has barely left the solar system. It crossed the heliopause, the boundary where the solar wind meets interstellar space, in 2012. But it has not reached the Oort cloud yet, a spherical shell of icy objects that marks the true edge of the sun's gravitational influence. The Oort cloud extends out to about 2 light years from the sun. At its current speed, Voyager 1 will not leave the Oort cloud for another 30,000 years. 30,000 years to cross our own solar system's outer boundary, and then it will enter interstellar space, the region between stars, which is even more empty than the space around our sun. The nearest star to our sun is Proxima Centauri, 4.2 light years away. That is 25 trillion miles. If Voyager 1 were heading in that direction, which it is not, it would take 73,000 years to get there, and the entire journey would be through almost perfect vacuum, with maybe one atom every few cubic meters, traveling through darkness, so complete that human eyes could not function in it. That is the space between stars. Mostly nothing. Occasionally a hydrogen atom, rarely a dust grain, almost never anything else. And yet, despite this incredible emptiness, we still call it space. We still think of it as a place, because it is. It is the largest place that exists. The space between things is bigger than the things themselves by an almost infinite margin. Imagine you could shrink the sun down to the size of a grain of sand. On that scale, Earth would be a speck of dust about 2 inches away. Jupiter would be a small pebble about 10 inches away. Neptune would be another small pebble about 5 feet away. And Proxima Centauri, the nearest star, would be another grain of sand about 10 miles away. 10 miles of emptiness between 2 grains of sand. That is how much space exists between stars. Now scale up to galaxies. Our Milky Way contains 200 to 400 billion stars. That sounds crowded, but the average distance between stars in our galaxy is about 5 light years. That is 30 trillion miles of emptiness between neighbors, and galaxies themselves are separated by even larger distances. The Andromeda Galaxy, our nearest large galactic neighbor, is 2.5 million light years away. That is 15 quintillion miles of almost nothing. The largest structures in the universe are galaxy clusters and superclusters, giant collections of hundreds or thousands of galaxies bound together by gravity. But even within those clusters, the space between galaxies is immense, and between the superclusters, there are cosmic voids, regions hundreds of millions of light years across, containing almost no galaxies at all, just empty space, cold, dark, silent, stretching on forever. This is the universe we live in, more nothing than something, more emptiness than matter, more silence than sound. And speaking of sound, there is none, not in space. Sound requires a medium to travel through. It needs molecules to bump into other molecules, creating pressure waves that our ears detect as noise. But space does not have enough molecules for sound to propagate. The density is too low. If you screamed in space, the sound waves would die within a few centimeters of your mouth because there is nothing for them to travel through. You could be next to an exploding star and hear nothing, just silence. That silence is one of the strangest things about space. On Earth, we are never truly in silence. There is always background noise, air moving, distant traffic, other people, our own heartbeat and breathing. But in space, there is perfect silence, the kind of quiet that does not exist on Earth, because there is always some medium for sound to travel through. In space, silence is absolute. Astronauts who have done spacewalks talk about this. The silence is overwhelming at first, unnatural. They can hear their own breathing in their spacesuits, their own heartbeat, but nothing else. No wind, no birds, no hum of distant machinery, just their own biological sounds and nothing more. Some find it peaceful, some find it unsettling, but everyone finds it profound. And that silence extends across the entire universe. No matter how violent an event, no matter how much energy is released, it happens in complete silence. Stars explode silently. Black holes collide silently. Galaxies merge over billions of years without making a sound. The universe is a silent film, all action and no audio. This emptiness and silence might seem frightening. It might make space feel hostile, alien, wrong. But I think there is something deeply calming about it, something that helps put everything into perspective. The universe is mostly empty. It does not need to be full. It does not need to be busy. It does not need to rush or make noise or prove anything. It just exists patiently across vast distances and vast stretches of time. And in that emptiness, occasionally, matter comes together to form something interesting, a star, a planet, a living thing. And then, eventually, it disperses again, back to emptiness, back to silence. We live on a tiny island of matter, in an ocean of nothing. Earth is a small rock, 8,000 miles in diameter, surrounded by millions of miles of vacuum. The atmosphere that keeps us alive is only about 60 miles thick. Above that, emptiness. Below our feet, we have maybe 4,000 miles of solid and liquid rock before reaching the center, but in every direction outward, the emptiness extends essentially forever. And yet, we worry about things. We stress about deadlines, about money, about what other people think. We fight over resources, over ideas, over pieces of land. We spend our lives in constant motion, constant noise, constant activity, and all of it happens on this tiny speck of matter floating through an incomprehensibly large void. The universe does not care about our stress. It does not care about our schedules or our achievements or our failures. It just continues being mostly empty, mostly silent, mostly patient, and there is a lesson in that, a reminder that we do not need to fill every moment with activity, every silence with noise. We can just be. We can exist without constantly doing, constantly producing, constantly moving. The emptiness of space is not a void that needs to be filled. It is a feature, not a bug. It gives things room to exist. It allows light to travel unimpeded for billions of years. It permits galaxies to form and evolve without constantly colliding. The space between things is just as important as the things themselves, maybe more important. Lao Tzu wrote that we shape clay into a pot, but it is the emptiness inside that makes it useful. We build walls to make a room, but it is the empty space within that we live in. The universe understands this. The universe is mostly empty because emptiness has value. It gives things room to be. It allows change. It permits motion. Without the vast emptiness of space, light could not travel, sound might exist, but it would be constant, chaotic, overwhelming. Matter would be compressed together, unable to form distinct structures. There would be no stars, no planets, no life. The emptiness is not an absence, it is a presence. It is the stage on which everything else performs. And in that emptiness, we find perspective. When you understand how much nothing exists, how rare matter is, how unlikely it is for atoms to come together in any organized form, let alone a living form, let alone a conscious form, you start to appreciate how precious existence is. You are a temporary organization of matter in an ocean of emptiness. You are rare. You are special, not because the universe planned it that way, but because the odds against you existing were astronomical, and yet here you are. The vastness and emptiness of space does not diminish us, it elevates us. We are the universe's way of creating complexity out of simplicity, structure out of chaos, consciousness out of atoms. We are islands of improbable organization in a sea of probable disorder, and that is beautiful. So tonight, as you lie in your bed on your small planet in the vast emptiness, remember that you are surrounded by almost nothing, and that almost nothing extends for trillions of miles in every direction. But right here, right now, in this one small spot, matter came together to form you. Atoms that could have drifted apart forever instead chose to be part of something organized, something alive, something conscious. The universe is mostly empty, but wherever you are, that spot is full. That spot contains matter, energy, thought, feeling. That spot matters, even if the universe does not care whether it exists or not. Rest now in the great emptiness. Let the silence of space remind you that peace is always available. You do not need to fill every moment. You do not need to prove your existence. You can just be, floating through the void on your small rock, temporarily organized, temporarily aware, temporarily part of the cosmic dance. The emptiness is patient. The silence is eternal. And you, briefly, wonderfully, impossibly, are here. You are spinning, right now, not metaphorically. Literally, you are rotating at about 1,000 miles per hour. The ground beneath you, the building around you, the air you breathe, all of it is moving at roughly the speed of sound. Earth rotates on its axis, completing one full turn every 23 hours, 56 minutes, and 4 seconds. That is not a day. That is a sidereal day, the actual time it takes for Earth to spin once relative to the distant stars. We rounded it to 24 hours for convenience, but the true rotation period is slightly shorter. And yet you feel nothing, no wind, no dizziness, no sense of motion at all. You lie in your bed, completely still, while hurtling through space at incredible velocity. The rotation is so smooth, so constant, so perfectly balanced that your body has no way to detect it. There is no reference point, no change in speed, no acceleration to trigger your inner ear. You just spin, silently, endlessly, without ever knowing it. This is one of the strange truths about living on a planet. Motion that never changes feels like stillness. We are always moving, but because the movement is consistent, we perceive it as rest. Earth has been spinning for 4.5 billion years, and it has never stopped, not even for a fraction of a second. The same rotation that started when our planet first coalesced from dust and gas continues today, unchanged, unstoppable. But Earth is not the only planet that spins. Every planet in our solar system rotates. Each one has its own rhythm, its own pace, its own particular way of turning through space. And when you compare them, you start to see personality in these cosmic objects. Some spin fast, some spin slow, some spin backwards. Each rotation tells a story about the planet's history, about collisions and gravitational interactions, and the random chaos of planetary formation. Let me tell you about Venus first, because Venus is strange. Venus rotates more slowly than any other planet in our solar system. One full rotation takes 243 Earth days. That is longer than a Venusian year, which is only 225 Earth days. Venus completes an entire orbit around the Sun faster than it completes one spin on its axis, which means if you could stand on the surface of Venus, which you cannot because it is hot enough to melt lead and the atmospheric pressure would crush you instantly. But if you could, you would see the sun rise in the west, slowly crawl across the sky for 117 Earth days, set in the east, and then experience 117 days of darkness before it rose again in the west. Why does Venus rotate so slowly? We think a massive collision early in the planet's history might have slowed its rotation dramatically, or perhaps tidal forces from the sun gradually locked Venus into this strange pattern. We do not know for certain, but we know Venus is different. It even rotates backwards compared to most other planets. While Earth spins counterclockwise when viewed from above the North Pole, Venus spins clockwise. Retrograde rotation, astronomers call it. Venus goes its own way. Mercury also rotates slowly, but for a different reason. One Mercury day equals 59 Earth days. But here is where it gets interesting. Mercury orbits the Sun in 88 Earth days, which means it completes exactly 3 rotations for every 2 orbits. This is called spin-orbit resonance, and it happened because the Sun's gravity gradually slowed Mercury's rotation over billions of years. The tidal bulge Mercury creates in response to the Sun's gravity acts like a brake, steadily reducing the rotation rate until it locked into this stable pattern. If you stood on Mercury's surface, you would experience the strangest days imaginable. The sun would rise, then appear to stop, then reverse direction and set on the same horizon it rose from, then rise again and continue across the sky. This happens because Mercury's orbital speed changes as it moves closer and farther from the Sun in its elliptical orbit. At certain points, the orbital motion temporarily overtakes the rotational motion, making the Sun appear to move backwards. Now let us talk about the fast spinners. Jupiter, the largest planet in our solar system, rotates faster than any other despite its enormous size. One Jupiter day lasts only 9 hours and 56 minutes. Think about that. A planet 11 times wider than Earth completes a full rotation in less than 10 hours. The equatorial regions move at 28,000 miles per hour. That incredible rotational speed creates intense winds, drives massive storms like the Great Red Spot, and causes the planet to bulge noticeably at its equator. Saturn spins almost as fast. One Saturn day is 10 hours and 33 minutes. That rapid rotation also flattens Saturn at the poles and bulges it at the equator, giving it the most oblate shape of any planet. If you could somehow compress Saturn down to the size of a basketball, it would look slightly squashed, wider than it is tall. The rotation literally reshapes the planet. Earth's rotation at 23 hours and 56 minutes sits comfortably in the middle, not too fast, not too slow, just right for life to evolve and thrive. And that rotation has been slowing down very gradually for billions of years. The moon's gravity creates tidal bulges in Earth's oceans and even in the solid rock of the planet itself. Those bulges act as a brake, slowing Earth's rotation by about 1.7 milliseconds per century. That does not sound like much, and it is not in human timescales, but over billions of years, it adds up. When Earth first formed, a day might have been only 6 hours long. When the first life appeared in the oceans 3.5 billion years ago, a day was probably about 12 hours. When dinosaurs walked the Earth 200 million years ago, a day was roughly 23 hours, and in another 100 million years, a day will be about 25 hours long. The moon is responsible for this gradual slowdown, but the moon is also moving away from Earth as a result, gaining about 1.5 inches per year. This is conservation of angular momentum in action. Earth's rotation slows, and that rotational energy transfers to the moon, pushing it into a higher orbit. Eventually, billions of years from now, Earth's rotation will slow enough that one side always faces the moon, the same way one side of the moon always faces Earth. The Earth and moon will be tidally locked to each other, rotating in perfect synchronization. But that will not happen for a very long time. For now, Earth continues its steady spin, day after day, year after year, never stopping, never changing pace significantly enough for us to notice. Mars rotates at almost the same rate as Earth. One Martian day called a sol lasts 24 hours and 37 minutes, close enough to an Earth day that astronauts who operate Mars rovers have to adjust their sleep schedules to Martian time. They work on Mars time, living on a planet they have never visited, synchronizing their lives with a rotation happening 140 million miles away. Uranus has the strangest rotation axis in the solar system. While most planets spin roughly upright, with their axis tilted only slightly from perpendicular to their orbital plane, Uranus is tilted 98 degrees. It essentially rolls along its orbit like a barrel instead of spinning like a top. This means that during parts of its 84-year orbit, One pole faces the sun continuously for 42 years, while the other pole experiences 42 years of darkness. Then they switch. The rotation period itself is about 17 hours and 14 minutes, but that rotation happens sideways. We think Uranus was knocked on its side by a massive collision early in the solar system's history. Something planet sized must have hit Uranus hard enough to tip it over, but not hard enough to destroy it. That collision happened billions of years ago, but Uranus still carries the scar, still rotates at that bizarre angle, still experiences seasons unlike any other planet. Neptune rotates in 16 hours and 6 minutes, fast enough to create powerful winds that reach 1,200 miles per hour, the fastest in the solar system. Those winds blow in the opposite direction of the planet's rotation, driven by internal heat rising from the core and interacting with the rapid spin. Neptune is the farthest planet from the Sun, receiving almost no solar energy, yet it radiates more heat than it receives. That internal heat source, combined with rapid rotation, creates weather patterns more extreme than anywhere else we know. All these rotations began the same way, when the solar system formed from a collapsing cloud of gas and dust. That cloud had angular momentum. It was rotating slowly. As the cloud collapsed, conservation of angular momentum caused it to spin faster, the same way an ice skater spins faster when they pull their arms in. The cloud flattened into a disk, and within that disk, planets formed. Each planet inherited some of the original rotation, modified by collisions, gravitational interactions, and tidal forces over billions of years. And here is what strikes me about all this. Here is what keeps me awake at night, or helps me fall asleep, depending on how you look at it. These rotations are ancient. They are older than life, older than oceans, older than continents. The spin you feel right now, or rather do not feel, connects you directly to the birth of the solar system. Earth has been rotating in essentially the same way for 4.5 billion years. The sun rises in the east and sets in the west today exactly as it did when Earth first solidified from molten rock. The day-night cycle that governs your sleep, that determines when you wake and when you rest, is the same cycle that has governed every living thing that has ever existed on this planet. Life evolved to match Earth's rotation. Our circadian rhythms, the internal biological clocks that make us sleepy at night and alert during the day, developed in response to this 24-hour cycle. Plants open their leaves during the day and close them at night, synchronized to the rotation. Animals hunt, sleep, migrate, reproduce, all timed to the rhythm of Earth's spin. Even bacteria show circadian patterns. The rotation is so fundamental, so constant, that life built itself around it. And because the rotation never changes significantly, not in timescales that matter to individual organisms, it creates the illusion of stability. The sun always rises. The sun always sets. Day follows. Night follows day in an endless pattern so reliable we base our entire concept of time around it. We measure our lives in days, in sunrises and sunsets, in the turning of our planet beneath our feet. But that rotation is not eternal. It is slowing down. In a few billion years, when the sun swells into a red giant, Earth's rotation will have slowed considerably, and eventually, far in the future, the rotation might stop entirely or become tidally locked to the sun the same way the moon is locked to Earth. But that is so far away, so many billions of years that it might as well be never. For now, for as long as humans will exist, Earth will keep spinning at roughly the same rate it always has. There is comfort in that. Comfort in knowing that some things are constant. The stars may be dying, the universe may be expanding, time may be relative and strange. But Earth keeps spinning, the sun keeps rising, the pattern holds, day after day, year after year, eon after eon. The rotation is one of the few things in the universe you can truly rely on. And tonight, as you lie still in your bed, remember that you are not still at all. You are spinning at 1,000 miles per hour. You are riding on a massive ball of rock, hurtling through space, turning endlessly, following the same motion it began billions of years ago. But that motion is so smooth, so constant, so perfectly balanced that you cannot feel it. It has become your baseline, your definition of stillness. Maybe there is a lesson there. Maybe the best kind of motion is the kind you do not notice, the kind that happens without effort, without struggle, without awareness. Earth does not try to rotate, it just does. And because it does, life exists. Days pass, time moves forward, everything continues. Rest now in the knowledge that the planet beneath you will keep turning. The sun will rise again tomorrow. The rotation will continue long after you are gone, carrying future beings through their days and nights, just as it carried every being that came before you. The spin is eternal, or close enough to eternal that it makes no difference. Sleep well on your spinning world. While Earth spins on its axis, it is also doing something else, something even more remarkable. It is falling constantly, endlessly. It has been falling around the sun for 4.5 billion years and will continue falling for billions more. But it is falling in such a precise way, at such a perfect speed, that it never hits the ground. It just keeps missing, over and over, tracing the same elliptical path through space that it has followed since the solar system formed. This is what an orbit is. Falling sideways fast enough that you miss the thing you are falling toward. Earth falls toward the sun at 67,000 miles per hour, but because it is also moving sideways at the same time, it curves around the sun instead of crashing into it. The sun's gravity pulls Earth inward. Earth's velocity carries it sideways. The combination creates a curved path that closes on itself, a loop, an orbit. And this has been happening for so long that it feels permanent. It feels like Earth is sitting still in space, when really it is moving faster than anything humans have ever built, faster than the fastest jet, faster than any rocket. You are traveling at 67,000 miles per hour right now, circling the sun, and you feel nothing because the motion is constant. No acceleration, no change, just smooth, endless falling. The orbit takes exactly 365.256 days to complete, not 365 days, which is why we have leap years. The extra quarter day adds up over 4 years, so we insert an extra day every fourth year to keep our calendars aligned with the seasons. But the orbit itself never varies. Earth completes its circuit around the sun with such precision that you could set a clock by it. Actually, we do set clocks by it. Our entire system of timekeeping is based on Earth's orbit. Johannes Kepler figured out how orbits work in the early 1600s. He studied decades of careful observations made by Tycho Brahe and discovered 3 laws that describe planetary motion. The first law states that planets orbit in ellipses, not perfect circles, with the Sun at one focus of the ellipse. Earth's orbit is very close to circular, but not quite at its closest point, called perihelion. Earth is about 91.4 million miles from the Sun. At its farthest point, aphelion, it is about 94.5 million miles away. The difference is only about 3%, which is why the orbit looks nearly circular. Interestingly, Earth reaches perihelion in early January and aphelion in early July, which means Earth is actually closest to the Sun during Northern Hemisphere winter. The seasons are not caused by distance from the Sun. They are caused by the tilt of Earth's axis. When the Northern Hemisphere tilts toward the Sun, it receives more direct sunlight and experiences summer, even though Earth might be farther from the Sun overall. Distance matters far less than angle. Kepler's second law describes how planets move faster when closer to the Sun and slower when farther away. This happens because angular momentum must be conserved. When Earth swings closer to the Sun at perihelion, it speeds up slightly. When it moves away to aphelion, it slows down slightly. The orbit is not a steady circle at constant speed. It is a dance, speeding up and slowing down in a rhythm that repeats every year. The third law relates orbital period to distance from the Sun. The farther a planet is from the Sun, the longer its orbit takes. Not just because it has a longer path to travel, but because gravity is weaker at greater distances. Mercury, closest to the Sun, orbits in only 88 Earth days. Venus takes 225 days. Mars takes 687 days. Jupiter takes 11.9 Earth years. Saturn takes 29.4 years. Uranus takes 84 years. Neptune takes 164.8 years. Neptune has only completed one full orbit since its discovery in 1846. Only one Neptunian year has passed in all of recorded human history of knowing that planet exists. When Neptune completes its second observed orbit in 2011, no one alive today who remembers its discovery will still be here. The orbit is that slow, that patient, that indifferent to human timescales. And yet, despite these vastly different orbital periods, the system is stable. The planets do not collide. They do not drift off into space. They have been orbiting the Sun for 4.5 billion years without major incident. Yes, there were collisions early in the solar system's history. The Moon probably formed from debris after a Mars-sized object struck Earth. Venus and Uranus likely suffered major impacts that affected their rotations. But those violent events happened billions of years ago. Since then, the orbits have settled into a stable configuration that will persist for billions more years. This stability comes from something called orbital resonance. Planets gravitationally influence each other, and over time, their orbits adjust into patterns where they rarely come close together. Jupiter and Saturn, for example, are in a 2 to 5 resonance. For every 2 times Jupiter orbits the Sun, Saturn orbits almost exactly 5 times. This means they return to the same relative positions repeatedly, but in a stable pattern that prevents close approaches. The asteroid belt between Mars and Jupiter shows gaps called Kirkwood gaps, regions where almost no asteroids exist. These gaps occur at orbital distances where asteroids would be in resonance with Jupiter. An asteroid in a 2-to-1 resonance with Jupiter would get a gravitational tug from Jupiter in the same part of its orbit every other lap. Over millions of years, those repeated tugs destabilize the orbit, sending the asteroid into a different path or ejecting it from the solar system entirely. The gaps are not empty because nothing ever formed there. They are empty because Jupiter cleaned them out over billions of years. This is the solar system teaching itself stability. Unstable orbits get perturbed and change. Stable orbits persist. After 4.5 billion years, what remains is a system of orbits that can last for billions more years without major changes. But here is something that might surprise you. Despite this stability, we cannot predict planetary positions perfectly beyond about 100 million years. This is not because our physics is wrong. It is because the solar system is chaotic, not chaotic in the sense of random or unpredictable on short timescales, but chaotic in the mathematical sense. Tiny differences in initial conditions lead to exponentially different outcomes over long periods. If you run a computer simulation of the solar system starting from today, and then run another simulation where you change Earth's position by 1 millimeter, the two simulations will match perfectly for a few million years. Then they start to diverge. After 100 million years, they show completely different planetary positions. This does not mean the orbits are unstable. Both simulations show stable orbits, but we cannot say exactly where the planets will be in their orbits 100 million years from now. The mathematics of chaos prevents us from making perfect long-term predictions. There is even a small chance that Mercury's orbit could become unstable in the next few billion years. Computer simulations show that gravitational perturbations from Jupiter could, under certain conditions, increase Mercury's orbital eccentricity enough to cause a collision with Venus or a fall into the Sun. The probability is low, maybe 1%, but it is not zero. The solar system is stable for now, but not perfectly stable forever. And yet, on human timescales, it might as well be eternal. The orbits have not changed noticeably in all of recorded history. Astronomers from Babylon could measure planetary positions 4,000 years ago, and those measurements match our predictions perfectly. The planets have traced the same paths for as long as humans have watched the sky. There is something deeply satisfying about that, something calming in a world where everything seems to change, where nothing feels permanent, where every day brings new uncertainty. The orbits persist. Earth will orbit the sun tomorrow exactly as it did today. The planets will continue their ancient dance, following paths carved out billions of years ago, indifferent to human concerns. We live our lives in the middle of this cosmic clockwork. The seasons change because Earth's tilted axis points in different directions as it orbits. Summer becomes fall, becomes winter, becomes spring, all because we are traveling around the sun on a tilted platform. The whole cycle of life on Earth, from planting to harvest, from migration to hibernation, from birth to death, all of it synchronized to Earth's orbit. And we're not just orbiting the sun. The moon orbits Earth. It takes 27.3 days to complete one orbit relative to the stars. But because Earth is also moving around the sun, it takes 29.5 days for the moon to return to the same phase. This is why lunar months are about 29 or 30 days long. The moon's gravity creates tides on Earth. High tide, low tide, twice a day, following the moon's position in its orbit. Coastal life evolved to match tidal rhythms. Some fish only spawn during spring tides, when the moon and sun align. Crabs time their activities to the tidal cycle. Even humans, living far inland now, still carry genetic echoes of tidal rhythms in our biology. Every planet with moons has created these smaller orbits within its own gravitational field. Jupiter has 95 known moons, each one following its own orbital path. The four largest, called the Galilean moons because Galileo discovered them in 1610, orbit in a beautiful resonance pattern. For every one orbit of Ganymede, Europa orbits twice and Io orbits 4 times. They return to the same configuration regularly, their mutual gravitational tugs keeping them locked in this stable dance. Saturn's rings are made of billions of individual particles, each one in its own orbit around the planet. Some ring particles orbit every 6 hours, others take days. The rings have gaps created by shepherd moons, small satellites whose gravity clears paths through the ring material. The whole system is an intricate ballet of gravitational interactions, stable over millions of years, but constantly shifting on smaller timescales. This is what orbits do. They create order out of chaos. They turn the random motions of the early solar system into predictable patterns. They allow planets to exist for billions of years without falling into the sun or flying off into space. They create seasons, tides, and cycles that life can evolve to match. And the mathematics is beautiful. Because Isaac Newton showed that gravitational orbits follow the same basic equations as any projectile motion. Throw a ball and it follows a parabolic arc. Throw it fast enough and the arc curves around Earth. Throw it even faster and it escapes Earth's gravity entirely. The difference between a baseball falling to the ground and the moon orbiting Earth is just velocity. Same physics, same principles, different speeds. Einstein later refined this understanding with general relativity, showing that gravity is not a force pulling objects together, but rather a curvature of spacetime itself. Massive objects, like the sun, curve spacetime around them, and planets follow the straightest possible paths through that curved space. Orbits are just objects following geodesics, the cosmic equivalent of straight lines in curved space. But for most purposes, Newton's simpler equations work perfectly. The orbit of Earth around the Sun can be calculated using math developed in the 1600s, and those calculations match reality to incredible precision. There is comfort in that precision, comfort in knowing that the universe follows rules, not arbitrary rules that change based on circumstances, but fundamental laws that apply everywhere, always. The same gravity that holds you to Earth also holds Earth to the Sun. The same momentum that keeps a spinning top upright also keeps planets in their orbits. The universe is consistent. It does not play favorites. It does not make exceptions. And so Earth continues its journey around the Sun, 67,000 miles per hour, 365.256 days per orbit. One astronomical unit from the Sun, tilted 23.5 degrees from vertical, following an ellipse with an eccentricity of 0.0167. All the numbers line up perfectly to create a planet where liquid water can exist, where temperatures allow complex chemistry, where life can emerge and thrive and eventually wonder about the orbit itself. Tomorrow Earth will be in a slightly different position in its orbit. The sun will rise a little earlier or a little later, depending on the season. The stars will have shifted slightly in the night sky, But the orbit continues. The dance goes on, and billions of years from now, long after humanity is gone, Earth will still be orbiting the sun, following the same path, falling forever around the star that gives it light. Sleep now, knowing you are held in place by gravity. You are part of an orbit within an orbit within an orbit. The moon orbits Earth. Earth orbits the sun. The sun orbits the center of the galaxy. And all of it moves with such precision, such mathematical perfection, that you can close your eyes and trust that everything will be exactly where it should be when you wake. Now let me tell you about the orbit you did not know you were making, the one that takes so long you will never complete it in your lifetime, the one your entire species will never complete, the orbit of our entire solar system around the center of the Milky Way galaxy. Right now, at this very moment, you are not just spinning on Earth and orbiting the sun. You are also hurtling through space at 514,000 miles per hour. The sun and everything bound to it gravitationally is moving in a massive orbit around the galactic center, and that orbit takes 225 million years to complete. 225 million years. Let that number settle in your mind for a moment. The last time our solar system was in its current position in the galaxy, dinosaurs had just begun to appear on Earth. The Triassic period was starting. The supercontinent Pangaea was intact. There were no flowers yet, no grass, no birds. The most advanced life forms were early reptiles and primitive mammal ancestors, and the sun was right here in this part of its galactic orbit. Since then, Earth has circled the sun 225 million times. Continents have drifted apart. Life has evolved through countless forms. Dinosaurs rose and ruled for 165 million years, then went extinct 66 million years ago. Mammals diversified. Primates appeared. Humans evolved. All of recorded history, every human civilization, every person who has ever lived, all of it happened while the sun moved through less than 1% of its current orbit. We call this orbital period a cosmic year. The sun has completed about 20 cosmic years since it formed 4.6 billion years ago, maybe 21. We are not entirely certain. The sun is middle-aged in terms of stellar lifespan, but young in terms of galactic orbits completed. It has only gone around the galaxy 20 times. That is all, and it will probably complete another 20 or 25 before it runs out of fuel and becomes a white dwarf. The center of the Milky Way lies about 26,000 light years from Earth. At the core sits a supermassive black hole called Sagittarius A*, about 4 million times the mass of the Sun. We cannot see it directly because too much dust blocks our view, but we can detect it by watching stars orbit around it. Those stars move so fast near the black hole, completing orbits in just a few years, that their motion proves something incredibly massive must be there. But we are far from the center, far from the black hole. Out here in what astronomers call the Orion Arm, or sometimes the Orion Spur, a minor spiral arm between two major arms. We live in the galactic suburbs, not in the dense, chaotic core where stars are packed millions of times more tightly than in our neighborhood, not in the empty outskirts where stars are sparse and lonely, right in the middle, in a quiet, stable region where the sun can orbit peacefully for billions of years. And the sun does not orbit alone. The Milky Way contains between 200 and 400 billion stars. We cannot count them exactly because many are hidden behind dust or too faint to detect, but hundreds of billions, at least, and all of them are orbiting the galactic center at different speeds depending on their distance. Objects closer to the center orbit faster, objects farther out orbit slower. This is the same principle that governs planetary orbits, but on a much larger scale. Mercury orbits the Sun faster than Earth. Earth orbits faster than Mars. Mars orbits faster than Jupiter. And in the galaxy, stars near the core orbit faster than the Sun, while stars farther out orbit slower. But here is where it gets strange. When astronomers first measured galactic rotation speeds, they expected to see the same pattern as the solar system. They expected stars farther from the center to orbit much slower than stars close in, following Newton's laws of gravity. But that is not what they found. Instead, they discovered that stars maintain roughly the same orbital speed regardless of distance from the center. Stars twice as far from the core as the Sun orbit at almost the same speed. Stars 3 times farther out also orbit at similar speeds. This should not happen if only visible matter existed in the galaxy. There is not enough mass in all the stars and gas we can see to create the gravitational pull needed to keep distant stars moving that fast. This observation led to the discovery of dark matter. There must be far more mass in the galaxy than we can see. Mass that does not emit light, mass that only interacts through gravity. Dark matter forms a massive halo around the galaxy, extending far beyond the visible disk. And it is this dark matter halo that keeps the galaxy rotating the way it does. We think dark matter outweighs visible matter by about 5 to 1 in the galaxy, which means most of the mass holding the Milky Way together is invisible. We orbit through a galaxy made mostly of something we cannot see, cannot touch, cannot detect, except by its gravitational effects. The universe keeps its secrets. But despite this mystery, the rotation continues. Steady, reliable, predictable. The Sun traces its path around the galactic center, taking 225 million years per lap, and it has been doing this since it formed. The orbit is so large that even moving at 514,000 miles per hour, it takes longer than life has existed on Earth to complete. And we are not alone in our orbital neighborhood. Thousands of stars within a few dozen light years orbit at roughly the same distance from the galactic center as we do. They form a loose stream of stars, all moving together, all following similar paths. Some are slightly faster, gradually pulling ahead. Some are slightly slower, gradually falling behind. But on cosmic timescales, we travel together. The nearest star, Proxima Centauri, is not stationary relative to us. It orbits the galaxy at a slightly different velocity. Right now, it is 4.2 light years away, but in about 27,000 years, it will make its closest approach to our solar system, passing within 3.1 light years. Then it will continue on its orbit, gradually moving away again. Stars pass by each other like ships in the night, each following its own trajectory, sometimes coming close, sometimes drifting apart, but all orbiting the same galactic center. The spiral arms of the Milky Way are not solid structures. They are density waves, regions where stars and gas pile up temporarily as they orbit. Think of traffic congestion on a highway. Cars enter the jam, slow down, then exit and speed up again. The jam itself moves slower than the cars passing through it. Spiral arms work the same way. Stars enter the arm, slow slightly as they pass through the denser region, then exit and speed up. The arms appear solid when viewed from a distance, but they are actually just patterns created by orbiting stars. Our sun is currently between spiral arms. In a relatively sparse region, we pass through a major spiral arm every 100 million years or so as we orbit. When we do, the night sky becomes brighter with more nearby stars. Stellar nurseries in the spiral arms create massive, bright, short lived stars. Supernovae become more common. The rate of cosmic ray exposure increases. Some scientists think these passages through spiral arms might correlate with mass extinction events on Earth, though the evidence is not conclusive. For now, we are in a safe, quiet part of the galaxy. No nearby supernovae threatening us, no close encounters with massive stars, just a gentle orbit through mostly empty space, exactly the kind of stable environment where life can evolve over billions of years without major cosmic disruptions. The Milky Way itself is part of an even larger structure. It belongs to the local group, a collection of more than 80 galaxies bound together by gravity. Andromeda, the nearest large spiral galaxy, is the dominant member. The Milky Way is second largest, and dozens of smaller dwarf galaxies orbit both of them. And the entire local group is moving. We are falling toward the Virgo cluster, a massive collection of thousands of galaxies, about 53 million light years away. That motion adds another layer to our cosmic velocity. Not only are we orbiting within the Milky Way, but the Milky Way itself is moving through space, drawn by the gravity of nearby galaxy clusters. If you add up all these motions, Earth is moving through space at incredible speeds: 1,000 miles per hour from rotation, 67,000 miles per hour from orbiting the Sun, 514,000 miles per hour from the Sun's orbit around the galaxy, and about 1.3 million miles per hour from the local group's motion toward Virgo. The total velocity depends on direction, but Earth is moving at roughly 1.3 million miles per hour through the cosmic microwave background reference frame. 1.3 million miles per hour, and you feel none of it. You lie in your bed, perfectly still, while racing through space faster than anything humans have ever built. The motion is so smooth, so constant, so completely beyond your ability to perceive that it might as well not exist. Only through careful astronomical measurements and sophisticated physics can we even detect these motions. And here is what I find most remarkable about the galactic orbit. The Sun will complete its current cosmic year in another 225 million years. Earth will still be orbiting the Sun, assuming nothing catastrophic happens. Life will still exist, though in forms we cannot imagine, and the beings living then, if they are intelligent, if they look up at the stars, will see a slightly different night sky than we see now. Stars will have moved. Constellations will have changed shape. Some stars we see tonight will have died. New stars will have been born. The galaxy will have rotated enough that everything looks different. But the rotation itself will continue, patient and eternal, as it has for billions of years and will for billions more. There is something humbling about that, something that puts human concerns into perspective. We worry about tomorrow, next week, next year. We plan for decades, if we are lucky, But the galaxy works on timescales of hundreds of millions of years. It does not care about quarterly earnings or election cycles or human lifespans. It just rotates, slowly, patiently, following the same path it has followed for billions of years. And yet we are part of that rotation. Every atom in your body has been orbiting the galactic center for 4.6 billion years since the Sun and Earth formed. Those atoms have completed about 20 laps around the galaxy. They were here for the rise and fall of the dinosaurs. They were here when the first life emerged from the oceans. They were here when the moon formed from a massive collision, and they will be here for billions more years, continuing the orbit long after you are gone. You are a temporary pattern made of atoms that have been traveling through space for cosmic ages. Your consciousness, your memories, your sense of self, all of it is just a brief moment in the long journey of those atoms around the galaxy. And when your pattern dissolves, when you die, the atoms will continue without you. They will become part of the earth again, then perhaps part of other living things, but always orbiting, always moving, always part of the galactic dance. The galaxy rotates. The stars follow their paths. The sun completes its cosmic year, and all of it happens with such grace, such mathematical perfection, such elegant simplicity that you can close your eyes and trust the universe to continue doing what it has always done. Nothing is rushing. Nothing is panicking. The galaxy has all the time in the world. Yuli has more time than that. It has cosmic time, deep time, time measured in the lifetimes of stars rather than the lifetimes of humans. Rest now knowing you are part of this ancient rotation. You are orbiting with the sun, traveling through the galaxy at 500,000 miles per hour, completing a journey that began long before humans existed and will continue long after we are gone. The orbit is patient, the rotation is eternal, and you briefly, wonderfully, are along for the ride. The universe is not sitting still. I know we have talked about rotation and orbits and all the ways things move through space, but now I need to tell you about a different kind of motion, a motion that is not circular, a motion that does not loop back on itself, a motion that is taking everything away from everything else, slowly, gradually, but inexorably. The universe is expanding, not expanding into something, just expanding. Space itself is stretching, pulling galaxies apart, increasing the distance between them. And this has been happening since the Big Bang 13.8 billion years ago. It is still happening now. It will continue happening forever. In 1929, an astronomer named Edwin Hubble made one of the most important discoveries in the history of science. He was studying distant galaxies, measuring their light, when he noticed something strange. The light from those galaxies was shifted toward the red end of the spectrum. This is called redshift, and it happens when an object is moving away from you. The motion stretches the light waves, making them longer, shifting them toward red. But here is the remarkable part. Every galaxy Hubble looked at showed redshift, every single one. And the farther away a galaxy was, the faster it appeared to be moving away. This was not random. It was a pattern, a clear, undeniable pattern that could only mean one thing. The universe is expanding, and galaxies are being carried apart by that expansion. Imagine you have a balloon with dots drawn on it. As you inflate the balloon, the dots move away from each other. not because they are moving across the surface of the balloon, but because the surface itself is stretching. Every dot sees every other dot moving away. There is no center to the expansion, no privileged position. From any dot's perspective, all the other dots are receding. That is what is happening with galaxies. Space itself is expanding, and galaxies are embedded in that space, like raisins in rising bread dough. As the dough expands, the raisins move apart, not because they are pushing through the dough, but because the dough between them is growing. The rate of expansion is described by the Hubble constant, currently measured at about 67 to 73 kilometers per second per megaparsec, depending on which method you use to measure it. A megaparsec is 3.26 million light years, so for every 3.26 million light years of distance, space is expanding at about 67 to 73 kilometers per second. That does not sound very fast. 67 kilometers per second is only about 42 miles per second. But remember, that is per megaparsec. A galaxy that is 10 megaparsecs away is receding at 670 kilometers per second. A galaxy 100 megaparsecs away is receding at 6,700 kilometers per second. A galaxy a billion light years away is receding at a significant fraction of the speed of light. And the most distant galaxies we can see, galaxies more than 13 billion light years away, are receding faster than the speed of light relative to us. Not because they are moving through space faster than light, which is impossible, but because the space between us and them is expanding so much that the accumulated expansion adds up to superluminal recession velocities. This does not violate relativity. Nothing is moving faster than light through space, but space itself can expand at any rate. There is no speed limit on the expansion of space. Now, here is where it gets unsettling. Because the universe is expanding, and because that expansion is accelerating, most galaxies are moving away from us. And as they move away, their light gets more and more redshifted. Eventually, galaxies will be moving away so fast that their light can never reach us. They will cross what astronomers call the cosmic event horizon, the boundary beyond which objects are receding faster than light can travel through the expanding space between us. Once a galaxy crosses that horizon, it disappears from our observable universe forever. We will never see it again. No light from it will ever reach us. It effectively ceases to exist from our perspective. And this is already happening. There are galaxies right now that we can see, but we are seeing their light from billions of years ago. The galaxy as it exists today has already crossed the event horizon. We are watching its past, but its present is forever beyond our reach. Over time, more and more galaxies will cross this horizon. In a few 100 billion years, all galaxies outside our local group will have receded beyond visibility. The night sky will contain only the Milky Way and Andromeda and the dozen or so dwarf galaxies bound to them by gravity. Everything else will be gone, carried away by the expansion of space. Astronomers in the far future, assuming intelligent life still exists, will look at the sky and see only their local galaxy cluster. They will have no evidence that other galaxies exist, no way to detect the cosmic microwave background, no way to know the universe had a beginning. They will live in what appears to be a static, unchanging cosmos, containing only one galaxy cluster, surrounded by eternal darkness. They will not know what we know. They will not have the evidence we have. The universe will have expanded so much that it will have erased the proof of its own history. Future beings will look at the same universe and see something completely different, something that appears eternal and unchanging, when really it is just old and empty. We live in a special time, a time when the universe is old enough to have formed galaxies and stars and planets and life, but young enough that we can still see distant galaxies, still detect the cosmic microwave background, still piece together the history of the universe from the evidence available. In a sense, we are lucky. We exist during the brief window when the universe is observable, when evidence of its origin and evolution is still accessible. A few 100 billion years from now, that window will close. The universe will continue existing, but it will be lonely, empty, dark. Just a few galaxies bound together by gravity, surrounded by endless expanding emptiness. But that is far in the future. For now, we can still see thousands of galaxies through our telescopes. We can measure their distances, calculate their recession velocities, study their compositions. We can watch the universe expanding in real time, even if that expansion is too slow for any human to perceive in a single lifetime. The expansion rate has not always been the same. In the very early universe, during a period called inflation, space expanded exponentially fast. In a fraction of a second, the universe grew from smaller than an atom to larger than a galaxy. This rapid inflation smoothed out irregularities and created the relatively uniform universe we see today. After inflation ended, the expansion continued, but slower. For billions of years, gravity from all the matter in the universe was pulling back against the expansion, slowing it down. Scientists expected the expansion would eventually stop and reverse, causing the universe to collapse back into a big crunch. Or they expected it would slow down forever, but never quite stop, asymptotically approaching zero expansion rate. But in 1998, two teams of astronomers studying distant supernovae made a shocking discovery. The expansion was not slowing down, it was speeding up. The universe is expanding faster now than it was billions of years ago. This should not happen. Gravity should be slowing the expansion, but something is overpowering gravity. Something is pushing the universe apart. We call this something dark energy, though we have no idea what it actually is. We just know it exists because we can measure its effects. Dark energy makes up about 68% of the total energy content of the universe. Dark matter makes up 27%. Ordinary matter, the stuff stars and planets and people are made of, makes up only 5%. We live in a universe dominated by things we do not understand, and dark energy is winning. It is pushing galaxies apart faster and faster. Eventually, the acceleration will become so extreme that even gravitationally bound structures like galaxy clusters will be torn apart. In the far, far future, trillions upon trillions of years from now, dark energy might even rip apart galaxies, solar systems, planets, molecules, atoms. This hypothetical end is called the Big Rip, but we are not sure if that will happen. It depends on the exact nature of dark energy, which we do not know. For now, galaxies bound by gravity remain together. The Milky Way and Andromeda are actually moving toward each other at about 110 kilometers per second. They will collide in about 4.5 billion years, merging into a single large elliptical galaxy. This is happening because their mutual gravitational attraction is stronger than the expansion of space between them. On local scales, gravity dominates. Only on very large scales does the expansion of space become noticeable. But beyond our local group, every galaxy is moving away. The Virgo cluster, 53 million light years away, is receding at about 1,000 kilometers per second. The Coma cluster, 330 million light years away, is receding at about 7,000 kilometers per second. Distant galaxy clusters billions of light years away is receding at tens of thousands of kilometers per second. We are watching the universe pull itself apart, slowly, gently, inexorably, and there is nothing anyone can do about it. No force can stop the expansion. No technology can reverse it. The universe decided 13.8 billion years ago, at the moment of the Big Bang, that it would expand forever, and that decision is irreversible. It is strange to think about. Everything we see in the night sky is temporary, not just individual stars, which die after billions of years, but entire galaxies, which will eventually recede beyond visibility. The universe is not static, it is not permanent, it is changing, always changing, and that change is taking things away from us. In some ways, this is the ultimate form of cosmic loneliness. We are isolated in space and time. The nearest star is over 4 light years away. The nearest large galaxy is 2.5 million light years away, and most galaxies are so far away that we will never reach them, never visit them, never know what they contain. The expansion ensures that the vast majority of the universe is forever beyond our reach. Even if we could travel at the speed of light, which we cannot, we could only ever reach a tiny fraction of the galaxies that currently exist. Most are already receding faster than we could ever chase them. They are lost to us, gone, as unreachable as the past. And yet, there is something beautiful about this, something poetic. The universe is not holding on, it is letting go. It is releasing galaxies into the void, allowing them to drift apart, giving them space to exist independently. There is no clinging, no desperate attempt to stay connected, just a gentle, cosmic goodbye that takes billions of years to complete. We are living in the middle of that goodbye. Can still see distant galaxies, but they are already leaving. Their light reaches us now, but in the future it will not. They will fade from view, one by one, until only our local neighborhood remains. And then we will be alone, truly alone, in a universe that has expanded itself into darkness. But that loneliness is far in the future. For now, we have the entire observable universe to marvel at. Hundreds of billions of galaxies, each containing hundreds of billions of stars, trillions upon trillions of worlds, most of which we will never see, never know, never understand. All of it drifting apart, all of it moving away, all of it temporary. You are living in a universe that is falling apart. Not catastrophically, not violently, just slowly, patiently, inevitably. Space is expanding. Galaxies are receding. The cosmos is becoming emptier, darker, lonelier with each passing moment. And there is something calming about accepting that, about understanding that nothing lasts forever, not even galaxies, not even the ability to see other galaxies. Everything is temporary, everything changes, everything moves away eventually. The universe teaches us to let go, to accept impermanence, to find peace in the fact that nothing, Not even the cosmos itself stays the same. Galaxies drift apart, stars burn out, atoms disperse, and that is okay. That is how it should be. The universe is not meant to be eternal and unchanging. It is meant to evolve, to expand, to gradually transform into something different. Tonight, when you look up at the stars, remember that you are seeing a universe in motion, a universe expanding, a universe pulling itself apart so slowly that you cannot perceive it, but doing it nonetheless. The galaxies you see are already leaving. The light reaching your eyes is from the past, from a time when those galaxies were closer, when the universe was younger, when there was more time. But even as things drift apart, even as the universe expands into loneliness, we are still here, still conscious, still able to observe and understand. We exist during the brief moment when the universe is knowable, when evidence of its history is still visible, when we can piece together the story of where everything came from and where it is going. That is enough, more than enough. We are the universe looking at itself during the one era when looking is still possible, and when we finally close our eyes for the last time, the expansion will continue without us. Galaxies will keep receding, space will keep stretching, the universe will keep letting go. Rest now in the expanding cosmos. Tomorrow, those galaxies will be slightly farther away. Tomorrow, the universe will be slightly larger, and you will still be here, briefly watching it all unfold, part of the great letting go that began 13.8 billion years ago and will never end. Before we go any further, before we drift off into the peaceful darkness of sleep, I want you to consider something that should keep you awake for just a few more minutes. Something that makes the existence of life, of consciousness, of you lying in your bed right now seem impossibly unlikely. The universe should not work. Everything about it is balanced on a razor's edge. The fundamental constants of physics, the forces that govern matter and energy, all of it is tuned to such incredible precision that if any value were even slightly different, the universe would be completely hostile to life. No stars, no planets, no atoms, nothing. Let me show you what I mean. Start with gravity. Gravity is the weakest of the four fundamental forces, but it is the one that shapes the large-scale structure of the universe. It pulls matter together, creates stars and planets and galaxies. Without gravity, matter would just drift apart forever, never clumping into anything interesting. But gravity is incredibly weak. A small refrigerator magnet can overcome the gravitational pull of the entire Earth when it picks up a paperclip. The electromagnetic force is about 10 to the 36th power stronger than gravity. That is a 1 followed by 36 zeros. Gravity is so weak compared to the other forces that physicists still do not fully understand why. And yet, if gravity were even slightly stronger, the universe would be completely different. Stars would burn through their fuel much faster, collapsing within millions of years instead of billions. Life would not have time to evolve. If gravity were about 10% stronger, the sun would have burned out long before humans appeared on Earth. On the other hand, if gravity were weaker, stars might never form at all. Gas clouds would not collapse under their own weight. No stars means no fusion, no heavy elements, no planets, no life. The universe would just be a thin soup of hydrogen and helium spreading out forever. Gravity has to be exactly as strong as it is, or we do not exist. Now consider the electromagnetic force. This is what holds atoms together, what creates chemistry, what allows molecules to form. Without electromagnetism, there would be no atoms, no molecules, no solid matter, just loose protons and electrons floating around, never binding together. But the strength of electromagnetism also has to be precise. If it were slightly stronger, electrons would be bound too tightly to atoms. Chemical reactions would not happen. No chemistry means no life. If it were slightly weaker, electrons would barely bind at all. Atoms would fall apart. Again, no chemistry, no life. The electromagnetic force has a value called the fine structure constant, usually written as alpha, which is approximately 1 divided by 137. This number determines how strongly charged particles interact, and it has to be very close to 1 over 137 for the universe to work. If alpha were 1 over 140 instead of 1 over 137, carbon would not be stable. Carbon is the basis of all known life. Every living thing on Earth is built around carbon chemistry. If carbon were not stable, life as we know it could not exist. If alpha were 1 over 130, fusion in stars would not produce enough carbon in the first place. Stars would still exist, but they would not create the elements necessary for life. The fine structure constant has to be almost exactly what it is, or the universe cannot support complex structures. Then there is the strong nuclear force. This is what holds atomic nuclei together, binding protons and neutrons into stable configurations. Without the strong force, atomic nuclei would fly apart instantly. Only hydrogen would exist, single protons with no ability to form heavier elements. But if the strong force were about 2% stronger, protons would bind together so readily that all the hydrogen in the early universe would have fused into helium and heavier elements during the first few minutes after the Big Bang. No hydrogen means no water, no stars like the sun, and drastically different stellar evolution. Life would be impossible. If the strong force were about 5% weaker, deuterium, a heavy form of hydrogen, could not form. Without deuterium, there is no path to creating heavier elements in stars. The universe would be stuck with only hydrogen, no carbon, no oxygen, no life. The strong force has to be within about 2% of its actual value for the universe to create the chemistry we need. And then the weak nuclear force, responsible for radioactive decay and certain fusion processes. If it were stronger, the Big Bang would have converted too much hydrogen into helium. If it were weaker, supernovae would not explode properly, and heavy elements would not scatter through space. Four fundamental forces. All of them have to be almost exactly the strength they are. Change any one by a small amount, and the universe becomes sterile, lifeless, incapable of producing anything as complex as a human being. But it gets even more specific. Let us talk about Earth itself. Earth orbits at an average distance of 93 million miles from the Sun. This distance is not arbitrary. It places Earth in what astronomers call the habitable zone, or the Goldilocks zone, the region around a star where temperatures allow liquid water to exist on a planet's surface. If Earth were 5% closer to the Sun, about 88.3 million miles, instead of 93 million, temperatures would be too high. Water would evaporate. The greenhouse effect would spiral out of control, turning Earth into something like Venus, with surface temperatures around 900 degrees Fahrenheit. Nothing complex could survive. If Earth were 5% farther from the Sun, about 97.6 million miles, temperatures would be too low. Water would freeze permanently. The planet would become an ice ball, incapable of supporting the liquid oceans that life requires. Earth sits right in the middle, right where it needs to be, and it has remained roughly in this orbit for 4.5 billion years, giving life plenty of time to evolve and diversify. But the distance is not the only thing that matters. Earth's size is important too. Earth is large enough to have sufficient gravity to hold onto an atmosphere, but not so large that the atmosphere becomes crushingly thick like Jupiter's. If Earth were 50% more massive, the increased gravity would trap too much hydrogen and helium, creating a thick atmosphere hostile to life. If Earth were 50% less massive, it would not have enough gravity to hold on to lighter gases like water vapor, and the atmosphere would slowly leak into space. Earth's size is just right, and that size also determines the planet's internal heat. Earth has a molten iron core that generates a magnetic field. This magnetic field extends thousands of miles into space, creating the magnetosphere that deflects harmful solar wind and cosmic rays. Without this magnetic field, the sun would gradually strip away Earth's atmosphere. Mars lost most of its atmosphere this way after its magnetic field shut down billions of years ago. The magnetosphere exists because Earth is large enough to have a hot core that remains molten after 4.5 billion years. Smaller planets cool faster. Larger planets might have too much internal heat, leading to extreme volcanic activity. Earth is again just right. Then there is the moon. Earth's moon is unusually large compared to the planet it orbits. Most moons in the solar system are tiny compared to their planets, but the moon is about 1/4 the diameter of Earth, and it has profound effects on our planet. The moon's gravity creates tides in Earth's oceans. These tides mix nutrients, create intertidal zones where early life may have evolved, and help regulate ocean circulation. Without the moon, tides would be much weaker and the oceans would be more stagnant. More importantly, the moon stabilizes Earth's axial tilt. Earth is currently tilted 23.5 degrees relative to its orbital plane, and this tilt creates the seasons. But without the moon, gravitational perturbations from other planets would cause Earth's tilt to vary wildly over millions of years, swinging from 0 degrees to 85 degrees or more. These extreme variations would create catastrophic climate changes, making it difficult for complex life to survive. Mars has no large moon, and its tilt varies from 15 degrees to 35 degrees over a period of about 100,000 years. This causes extreme climate instability. Earth's tilt stays steady at about 23.5 degrees, varying by only about 1.3 degrees over a 41,000 year cycle, all because the moon is there, stabilizing us. The moon formed from a massive collision about 4.5 billion years ago. A Mars-sized object hit the young Earth, and the debris from that impact coalesced into the moon. This collision was random, unlikely, a cosmic accident, but without it, Earth would not have a moon, and without the moon, Earth's climate would be chaotic. We got lucky, incredibly, impossibly lucky. And then there is Jupiter. Jupiter orbits at 5.2 astronomical units from the Sun, far enough away that it does not disturb Earth's orbit, but close enough to act as a gravitational shield. Jupiter's enormous mass, 318 times Earth's mass, deflects comets and asteroids that would otherwise bombard the inner solar system. Computer simulations show that without Jupiter, Earth would suffer far more frequent impacts from large objects. The impact that killed the dinosaurs 66 million years ago might happen every few million years instead of every 100 million years. Intelligent life might never have time to evolve between catastrophic impacts. Jupiter acts as a cosmic vacuum cleaner, sweeping up debris and protecting Earth, and it just happens to be the right size, in the right orbit, at the right distance. If Jupiter were closer, its gravity would destabilize Earth's orbit. If it were farther away, it would not provide enough protection. If it were smaller, it would not deflect enough objects. If it were larger, it might perturb Earth's orbit. Over time, Jupiter is where it needs to be, and it is the size it needs to be for Earth to remain habitable for billions of years. Every detail matters. The composition of Earth's atmosphere, which is 78% nitrogen, 21% oxygen, and 1% other gases. If oxygen were much higher, wildfires would be uncontrollable. If oxygen were much lower, complex life could not metabolize enough energy. The atmosphere is balanced perfectly. The amount of water on Earth, covering about 71% of the surface. Too much water, and there would be no land for terrestrial life. Too little water, and the oceans would be too small to regulate climate and support marine ecosystems. Again, just right. The presence of plate tectonics, which recycles carbon through the Earth's crust and mantle, regulating carbon dioxide levels in the atmosphere over geological timescales. Without plate tectonics, carbon dioxide would accumulate in the atmosphere, creating a runaway greenhouse effect, or it would get locked in rocks permanently, cooling the planet into an ice age. Plate tectonics keeps the carbon cycle balanced, and plate tectonics only happen because Earth is the right size and has the right amount of internal heat. Most planets do not have plate tectonics. Venus does not. Mars does not. Earth does, and that makes all the difference. Everything had to line up. The fundamental forces had to be exactly the right strength. The sun had to be the right type of star, not too hot, not too cool, not too short-lived. Earth had to form at the right distance in the right-sized orbit. The moon had to form from a chance collision. Jupiter had to exist in the right place. The atmosphere had to evolve to the right composition. Plate tectonics had to develop and persist. Change any one of these factors, and Earth becomes uninhabitable. Change several, and the universe cannot produce anything like life anywhere. We live in a universe that seems designed for us, even though no one designed it. The constants just happen to have the values they do. The solar system just happens to be configured the way it is. And against all odds, here we are, conscious beings wondering why everything is so perfect. Scientists call this the fine-tuning problem. Why is the universe so precisely calibrated to allow life? Some argue it is evidence of a creator. Some argue it is just random luck, and we exist because in a universe with different constants, there would be no one to ask the question. Some argue there are infinite parallel universes with different constants, and we just happen to live in one of the rare ones where life is possible. No one knows the answer, but we know the facts. The universe is balanced on an impossibly thin line between sterility and complexity, and somehow, for reasons we do not understand, we ended up on the side where complexity is possible, where stars last long enough to create heavy elements, where planets can form in stable orbits, where water can exist as a liquid, where evolution can slowly build from simple molecules to conscious beings capable of understanding the universe itself. You are the product of billions of years of unlikely events. Your existence depended on stars forming, dying, creating elements, scattering them through space. It depended on the solar system forming with the right configuration. It depended on Earth having liquid water, a stable climate, a protective magnetic field, a large moon, and a guardian planet in the outer system. It depended on life emerging, surviving multiple mass extinctions, evolving into complex forms, eventually producing conscious thought. The odds against you existing are so astronomical that it should be impossible, and yet here you are. The universe created you anyway. It threaded the needle. It balanced on the edge. It maintained the precise conditions necessary for matter to organize itself into something that can think, feel, wonder, and fall asleep while contemplating the cosmos. That is what makes existence so precious. It should not work, but it does. And for reasons we may never fully understand, the universe gave us this brief moment of awareness, this opportunity to see, to know, to appreciate how unlikely and wonderful it all is. Rest now in the perfectly balanced universe. Tomorrow, the constants will still be tuned exactly right. The forces will still hold matter together. Earth will still orbit in the habitable zone, and you will wake up, still impossibly alive, still part of this cosmic accident that somehow, against all odds, went right. There is a phenomenon that happens to astronauts when they see Earth from space for the first time. Something shifts inside them, something fundamental about how they understand their place in the universe. Psychologists call it the overview effect, and every person who has experienced it describes it the same way: profound, life changing, humbling beyond words. From space, Earth looks different than any photograph can capture. It is not just the colors, though the blue of the oceans and the white of the clouds and the browns and greens of the continents are breathtaking. It is not just the size, though seeing the entire planet in one view is shocking after a lifetime of only seeing tiny pieces of it. It is something deeper, something that changes you. From space, Earth looks fragile. You can see how thin the atmosphere is, just a delicate blue film surrounding the planet, barely visible against the black void beyond. That atmosphere is only about 60 miles thick, and most of it, the breathable part, is concentrated in the bottom 10 miles. From space, you can see it as what it really is: a paper-thin shell protecting life from the hostile emptiness of space. Astronauts describe feeling a sudden awareness of how vulnerable Earth is, how small, how alone. There is nothing between us and the infinite darkness except that fragile layer of air. No backup planet, no escape, just one small world, spinning through the void, carrying every living thing we know about. And from that perspective, something else becomes clear. The borders disappear. On Earth, we see political boundaries everywhere: lines on maps, fences, walls. We divide the planet into countries, states, territories, each one claiming ownership of a piece of the surface. Wars are fought over these lines. People die defending or crossing them. National identity becomes central to how we see ourselves and others. But from space, none of that exists. You cannot see borders. There are no lines dividing nations, no markers showing where one country ends and another begins. There is just land, ocean, clouds, ice, a single continuous surface with no indication that humans have carved it into competing territories. Astronauts often say this is the most striking thing about seeing Earth from space. The realization that all the conflict, all the division, all the reasons we give for treating people differently based on where they were born, none of it has any physical reality. We made it all up. The borders only exist in our minds. From orbit, you see Earth as what it really is: one planet, one ecosystem, one interconnected system where everything affects everything else. Pollution released in one country blows into another, rivers cross borders. Ocean currents connect distant shores. The atmosphere does not recognize political divisions. Weather systems do not stop at national boundaries. We are all in the same small world, breathing the same air, drinking the same water that has been cycling through the Earth system for billions of years. We are all made of the same stardust, living on the same fragile rock, utterly dependent on the same thin layer of atmosphere to protect us from the vacuum of space. This realization, this sudden shift in perspective, is what the overview effect does to people. It makes the arbitrary divisions humans create seem absurd. It makes conflicts over resources seem short sighted. It makes nationalism feel like a failure of imagination, because from space, it is obvious that we are all in this together, whether we like it or not. There is nowhere else to go. This is it. This is home. The astronaut Edgar Mitchell, who walked on the moon during Apollo 14, described the experience like this. He said seeing Earth from the moon created an instant global consciousness, a people orientation, an intense dissatisfaction with the state of the world, and a compulsion to do something about it. He felt connected to every living thing on the planet in a way he had never felt before. Another astronaut, Ron Garan, said that from space you see the planet as it truly is, a beautiful, fragile oasis suspended in the hostile emptiness of space. And you realize that all of us, every single human being, every living creature, all of life, exists on this one tiny world. We are all earthlings. That is our primary identity. Everything else is secondary. This perspective is not available to most people. Only about 600 humans have ever been to space. Only 24 have traveled far enough to see Earth as a whole sphere, a distant blue marble floating in the dark. The rest of us, billions of people, live our entire lives on the surface, never seeing the planet from outside, never gaining that cosmic perspective. But even without going to space, we have photographs, and those photographs have changed how humanity sees itself. The most famous is probably the pale blue dot, taken by Voyager 1 in 1990 from a distance of 3.7 billion miles. At that distance, Earth is just a tiny speck, less than a single pixel in the image, a pale blue dot suspended in a beam of scattered sunlight. You have to squint to see it. You have to be told where to look. But once you see it, you cannot unsee it. That dot is Earth. That is where everyone you know lives. That is where every human who has ever existed was born, lived, and died. Every king and peasant, every creator and destroyer, every young couple in love, every mother and father, every inventor, explorer, scientist, artist, every saint and sinner, every civilization that rose and fell, all of it happened on that tiny dot, barely visible against the vastness of space. Carl Sagan, who advocated for Voyager to take that photograph, wrote about it beautifully. He said, "Earth is a mote of dust suspended in a sunbeam, that our posturings, our imagined self importance, the delusion that we have some privileged position in the universe, are all challenged by that point of pale light." He said, "Our planet is a lonely speck in the great enveloping cosmic dark, and that in all that vastness there is no hint that help will come from elsewhere to save us from ourselves." That last part is important. There is no backup planet, no cavalry coming to rescue us if we destroy the one world we have. We are alone, isolated, dependent entirely on this small, fragile oasis in the vast desert of space. The Apollo 8 astronauts were the first humans to see Earth from lunar distance, orbiting the moon on Christmas Eve, 1968. They watched Earth rise over the moon's horizon, a moment so powerful that astronaut Bill Anders took a photograph that became known as Earthrise. That image, showing the blue and white Earth hanging in the black sky above the gray lunar surface, is often credited with helping spark the environmental movement. For the first time, people could see Earth as a finite, delicate system rather than an infinite resource. The planet looks small, vulnerable, beautiful, but fragile. And seeing it that way changed how people thought about protecting it. Before spaceflight, humans never had a way to see Earth as a whole. We lived on the surface, traveling from place to place, but never seeing the bigger picture. We could imagine the planet as a sphere. We could draw maps, but we could not actually witness it the way astronauts do. Now we can, and that changes things. When you see Earth from space, you see no weapons, no armies, no signs of conflict, just a quiet, peaceful world floating in silence. The wars happening on the surface are invisible from orbit. The violence, the suffering, the struggles, all of it is hidden beneath the clouds. From space, Earth looks serene, calm, untouched by human drama. And that contrast is jarring. The planet looks so peaceful from above, while on the surface, humans fight and compete and divide themselves into groups. The disconnect between how Earth appears from space and how humans behave on its surface is stark. Some astronauts come back from space with a renewed sense of purpose, a desire to help humanity see what they saw, to share that perspective shift. Others struggle with the gap between the unity they felt in space and the division they see on Earth. It is hard to come back to politics and borders and nationalism after seeing the planet as a single interconnected whole. But whether or not you have been to space, whether or not you ever will, the message is clear. We all live on the same small world, the same pale blue dot, the same fragile oasis, and everything we do affects everyone else, whether we acknowledge it or not. The atmosphere does not care about borders. Climate change affects the entire planet. Pollution released in one region eventually spreads everywhere. Species extinction reduces biodiversity for the whole world. Nuclear war would affect every continent. We are connected whether we like it or not by the simple fact that we share one atmosphere, one ocean, one interconnected ecosystem, and that ecosystem is more fragile than it looks from the surface. From space, you can see deforestation. You can see the shrinking ice caps. You can see dust storms and smoke from fires and the lights of cities spreading across formerly dark land. You can watch humanity's impact on the planet in real time, visible even from orbit. The overview effect often comes with a sense of protectiveness. Astronauts say they want to shield Earth, to take care of it, because from space it looks so vulnerable. The planet cannot defend itself. It just exists, rotating peacefully, providing everything life needs, asking nothing in return. And yet we treat it carelessly, as if there were another one waiting if we ruin this one. There is not another one. This is it. This pale blue dot is the only home we have ever known, the only place in the entire universe where we know life exists, and it is small, so much smaller than we imagine when we are standing on its surface, surrounded by sky and land that seems to go on forever. But from space, the truth is obvious. Earth is tiny, isolated, finite, and we are all on it together, whether we feel connected to each other or not. Our fates are linked, our futures are shared. We succeed together or fail together because there is nowhere else to go. This perspective, this view from outside, the sudden understanding of our place in the cosmos, it is something humanity needs, not just astronauts, everyone. We need to see ourselves as Earthlings first, as inhabitants of a small planet in a vast universe, before we see ourselves as members of any particular nation or group. Because the divisions we create on the surface are not real in any cosmic sense. They are human inventions, useful perhaps for organizing societies, but ultimately arbitrary. From space, they do not exist. There is just Earth, just one planet, just home, and home is beautiful, breathtakingly beautiful. The blues of the ocean are deeper than any photograph can capture. The whites of the clouds swirl in patterns that reveal the invisible currents of the atmosphere. The greens and browns of the land show where life has taken hold, transforming barren rock into ecosystems that support billions of organisms. At night, you can see the lights of human civilization, cities glowing against the darkness, a testament to human ingenuity and creativity. During the day, you can see rivers and mountains and deserts and forests, all the natural wonders that make Earth unique in the solar system. And surrounding it all, that thin blue line, the atmosphere, the layer of air that makes everything possible, so thin you could cross it in a car in less than an hour if you could drive straight up, so fragile that it looks like it could be wiped away with a breath, and yet strong enough to have protected life for billions of years. From space, you understand that we are not outside nature, looking at it, using it. We are part of it, embedded in it, completely dependent on it. The air we breathe is part of the global atmosphere. The water we drink is part of the global water cycle. The food we eat comes from ecosystems that are part of the planet's interconnected biosphere. We are not separate. We are cells in the body of Earth, part of a larger living system. And that system, that beautiful blue world floating in space, is the only one we have. We were born here. We will die here. And everything we care about, everyone we love, exists on that small sphere, rotating peacefully, waiting for us to realize how precious it is. Tonight, as you lie in your bed on the surface of this planet, remember that you are on a spaceship, a natural spaceship orbiting the sun, traveling through the galaxy, carrying all of life with it. Earth is a vessel moving through space, and we are its passengers. There is no escape, no other world nearby, just this one, with its thin atmosphere and liquid oceans and perfect conditions for life. We are all astronauts, really, all of us traveling through space together. The only difference is that most of us never leave the surface, never see Earth from outside, never gain that cosmic perspective. But the truth remains, whether we see it or not. We are one species on one planet, in one solar system, in one galaxy, in an infinite universe. And this planet, this pale blue dot, is worth protecting, worth cherishing, worth seeing for what it really is. Not a collection of divided nations competing for resources, but one interconnected world supporting all known life, floating through the void, irreplaceable and infinitely precious. Sleep well on your small planet. Tomorrow it will still be here, still rotating, still providing everything you need, still home, the only home we have ever known, the only home we will ever have. Look up at the moon tonight, and you are seeing Earth's oldest companion, or only natural satellite, a world that has been with us for 4.5 billion years, silently orbiting, gently tugging, shaping our planet in ways most people never think about. The moon is not just a light in the night sky. It is not just a romantic backdrop or a curiosity to observe through telescopes. The moon is essential to Earth as we know it. Without the moon, Earth would be a fundamentally different planet. Life might not have evolved at all, and if it had, it would have evolved into something completely alien to what we see today. Let me tell you how the moon shapes our world. Every day, twice a day, the moon creates tides in Earth's oceans. The moon's gravity pulls on the water, creating a bulge on the side of Earth facing the moon. There is also a bulge on the opposite side, created by inertial forces as Earth and Moon orbit their common center of mass. As Earth rotates beneath these bulges, the water level at any given location rises and falls. High tide, low tide, high tide, low tide. The rhythm repeats endlessly. This might seem like a minor effect, water going up and down a few feet twice a day, but the consequences are enormous. Tidal zones, the areas of coastline that are underwater at high tide and exposed at low tide, are some of the most biologically productive environments on Earth. Nutrients from the land wash into the ocean. Nutrients from the ocean concentrate in shallow pools. Organisms adapted to both aquatic and terrestrial environments thrive here. Many scientists think life might have first emerged from the oceans in tidal zones, where the changing water levels created opportunities for adaptation. Without the moon, tides would still exist because the sun also creates tidal forces, but solar tides are only about one-third the strength of lunar tides. Without the moon, tides would be much weaker, tidal zones would be much smaller, and coastal ecosystems would be drastically different. Perhaps life would have taken longer to colonize land. Perhaps it would have happened differently, or perhaps not at all. But tides do more than just create habitats. They also affect Earth's rotation. The tidal bulges created by the moon do not line up perfectly with the Earth-Moon axis. Earth rotates faster than the moon orbits, so the tidal bulges are dragged ahead of the moon's position by Earth's rotation. These misaligned bulges create a gravitational torque that acts as a brake on Earth's rotation. The effect is tiny, but relentless. Earth's rotation is slowing by about 1.7 milliseconds per century. That does not sound like much. You will never notice it in your lifetime, but over millions and billions of years, it adds up. When Earth first formed, a day was only about 6 hours long. The planet was spinning much faster than the moon formed, probably from debris after a Mars sized object collided with the young Earth. And immediately, the moon began slowing Earth's rotation through tidal forces. 4 billion years ago, a day was about 12 hours. When the first complex life appeared in the oceans 600 million years ago, a day was roughly 22 hours. When dinosaurs roamed the earth 200 million years ago, a day was about 23 hours. And in another 100 million years, a day will be about 25 hours. The slowing is not uniform. It varies depending on the distribution of Earth's mass, changes in ocean currents, and other factors. But the overall trend is clear. Earth is gradually losing rotational energy, and the moon is responsible. But where does that energy go? Energy cannot be destroyed, only transferred, and the moon receives it. As Earth's rotation slows, the moon moves farther away. The rotational energy lost by Earth is converted into orbital energy for the moon. The moon is currently receding from Earth at a rate of about 1.5 inches per year. That is roughly the rate your fingernails grow. Again, it seems insignificant, but over billions of years, the effect is dramatic. When the moon first formed, it was probably only about 15,000 miles from Earth. Now it is about 238,855 miles away. It has been moving away from Earth for its entire existence. In the early days when the moon was much closer, tides were enormous. Some estimates suggest tides might have been hundreds of feet high, creating massive tidal bores that swept across the coastlines. The early Earth was a violent, dynamic place, with the moon dominating the sky, appearing 15 to 20 times larger than it does today. As the moon moved away, tides became gentler. The day lengthened, and Earth settled into the stable rhythm we experience now. But the moon is still moving away. In about 600 million years, it will be far enough that total solar eclipses will no longer be possible. The moon will appear too small to completely cover the sun. This is a lucky time for humanity. We exist during the brief window when the moon and sun appear almost exactly the same size in the sky, making total solar eclipses possible. Our descendants, if they exist, will never see what we can see. And in billions of years, the moon will be so far away that its tidal effects will be minimal. Earth's rotation will have slowed so much that one side of the planet will always face the moon, just as one side of the moon already faces Earth. This is called tidal locking, and it is the eventual fate of the Earth-Moon system. But that is so far in the future, so many billions of years away, that it does not really matter. The sun will become a red giant long before then, probably engulfing both Earth and moon. The tidal locking will never complete. For now, the moon orbits at a comfortable distance, creating moderate tides, gradually slowing our rotation and providing one of the most important stabilizing forces in the solar system. Let me explain that last part, because it is crucial. Earth's rotational axis is tilted 23.5 degrees relative to its orbital plane around the sun. This tilt is what creates the seasons. When the northern hemisphere tilts toward the sun, it is summer in the north and winter in the south. 6 months later, the southern hemisphere tilts toward the sun and the seasons reverse. But that 23.5-degree tilt is not fixed. It wobbles slightly over a period of about 41,000 years, varying between 22.1 and 24.5 degrees. This variation is small, and it is regular. The climate changes somewhat over those 41,000 years, but life adapts. The variation is predictable. Mars, in contrast, has no large moon. It has two tiny moons, Phobos and Deimos, but they are so small that they provide almost no stabilizing influence. As a result, Mars's axial tilt varies wildly over time. Simulations show that Mars's tilt can swing from nearly 0 degrees to as much as 60 degrees or more over periods of millions of years. When Mars's tilt is low, the poles receive very little sunlight, and ice accumulates there. When the tilt is high, the poles receive direct sunlight during summer, the ice melts, and the atmosphere thickens temporarily before freezing out at other locations. The climate swings between extremes. Complex life would have a very difficult time evolving on a planet with such chaotic climate variations. Life needs stability. It needs predictable patterns. It needs time to adapt. Mars does not provide that because it has no large moon to stabilize its axis. Earth does. The moon's gravity acts on Earth's equatorial bulge, creating a gyroscopic stabilization effect. The tilt still wobbles, but only by a few degrees over tens of thousands of years. Life can adapt to that. Life can thrive under those conditions. Without the moon, Earth's tilt could vary as much as Mars's does. Seasons would be unpredictable. Ice ages would come and go erratically. The climate would swing between extremes. Complex life would struggle to survive. The moon does not just light up our nights, it stabilizes our planet. It makes Earth habitable, and it has been doing this job for 4.5 billion years without complaint, without recognition, just silently orbiting, gently tugging, keeping everything balanced. The moon also has another effect that most people never consider. It creates the lunar cycle, the 29.5-day period from new moon to full moon and back to new moon. This cycle has been embedded in Earth's environment for so long that many organisms have evolved to respond to it. Some fish spawn only during full moons or new moons. Some coral species release their eggs and sperms simultaneously during specific lunar phases, increasing the chances of successful fertilization. Some crabs time their reproductive cycles to the tides, which are controlled by the moon. Even some plants show lunar rhythms in their growth patterns. Humans, too, may have evolved some responsiveness to the lunar cycle, though the evidence is mixed and controversial. But there is no doubt that the moon has been a constant presence in the night sky for as long as humans have existed, influencing culture, mythology, calendars, and timekeeping. Many ancient cultures used lunar calendars, dividing the year into months based on the moon's phases. The word month itself comes from moon. The human menstrual cycle averages about 29.5 days, the same as the lunar cycle, though whether this is coincidence or the result of evolutionary pressure is still debated. What is clear is that the moon has shaped Earth in profound ways. It has influenced the evolution of life. It has stabilized the climate. It has created tides that mix nutrients and shape ecosystems. It has slowed Earth's rotation to a comfortable 24 hours. It has given us regular seasons and predictable weather patterns. And it did all this by accident. The moon was not placed in orbit around Earth for our benefit. It formed from a catastrophic collision, a random event in the chaos of the early solar system. But that random event turned out to be one of the most fortunate accidents in the history of life. Without the moon, Earth would still exist. It would still orbit the sun. It would still have water and atmosphere. But it would be a different world, a harsher world, a less stable world, a world where complex life might never have emerged, or might have emerged in forms so alien we would not recognize it. We are lucky to have the moon, lucky that it is the right size, lucky that it orbits at the right distance, lucky that it formed at all. Most planets do not have large moons. Mercury and Venus have none. Mars has two tiny captured asteroids. Even the gas giants, with their dozens of moons, do not have any that are as large relative to the planet as our moon is to Earth. Earth's moon is unusual. It is 1/4 the diameter of Earth, massive enough to create significant gravitational effects, but not so massive that it destabilizes the system. It is a perfect companion, balanced precisely, providing exactly the influence Earth needs to remain habitable. Tonight, when you look up and see the moon hanging in the sky, remember that it is not just a distant rock. It is part of Earth's system, part of what makes this planet work. It has been with us since the beginning, shaping our world, stabilizing our climate, creating the conditions that allowed life to evolve and thrive. The moon is our partner in the cosmic dance. Earth and moon orbit their common center of mass, locked in a gravitational embrace that has lasted for billions of years. The moon is slowly moving away, but it will never truly leave. It will always be there, always orbiting, always tugging gently at our oceans and our planet. And as you drift off to sleep, you know that the moon is out there right now, pulling at the water in the oceans, keeping Earth's axis stable, slowing our rotation by imperceptible amounts, just as it has done every night since the solar system formed. The moon is patient. The moon is reliable. The moon is home's companion. Rest easy under the gentle influence of our ancient satellite. Tomorrow the tides will rise and fall again. Tomorrow the moon will be slightly farther away than it is today. Tomorrow the day will be infinitesimally longer, and all of it will happen so slowly, so gently, that you will never notice. But the moon will be there, doing its work, keeping Earth stable, making life possible. The universe gave us the moon, a gift we did not earn, a companion we did not ask for, but one we could not live without. Sleep well beneath its light. While our moon keeps Earth stable, other planets have moons that hide secrets beneath their frozen surfaces, worlds covered in ice, appearing dead and lifeless from the outside, but potentially harboring vast oceans beneath their crusts, oceans that might contain life. Life that evolved completely independently from Earth, life that would prove we are not alone in the universe. Let me take you to Europa first, one of Jupiter's 4 large moons, discovered by Galileo in 1610. Europa is slightly smaller than our moon, with a diameter of about 1,940 miles. From a distance, it looks like a smooth ball of ice, crisscrossed with reddish-brown streaks and cracks. But that ice is not solid all the way through. Beneath a crust estimated to be 10 to 15 miles thick, Europa hides an ocean of liquid water, and that ocean is enormous. Scientists estimate Europa's ocean contains twice as much water as all of Earth's oceans combined, twice as much. On a moon 1/4 the diameter of Earth, the ocean might be 40 to 100 miles deep, dwarfing Earth's deepest ocean trenches. It is one of the largest bodies of liquid water in the entire solar system. But how can water remain liquid so far from the Sun? Jupiter is 5.2 astronomical units away. Sunlight there is 27 times weaker than on Earth. Surface temperatures on Europa average about negative 260 degrees Fahrenheit. Everything should be frozen solid. The answer is tidal heating. Europa orbits Jupiter in a slightly elliptical orbit, and it is also gravitationally influenced by the other large moons, Io and Ganymede. These gravitational forces stretch and squeeze Europa as it orbits, generating internal friction, enough heat to keep the subsurface ocean liquid despite the frigid temperatures on the surface. This is the same process that makes Io, the innermost large moon, the most volcanically active body in the solar system. But Europa experiences less tidal heating, just enough to maintain liquid water without creating the extreme volcanism seen on Io. The surface of Europa shows clear evidence of this subsurface ocean. The ice crust is young, geologically speaking, probably only 40 to 90 million years old. It is constantly being renewed and resurfaced. Long cracks called lineae crisscross the moon, and some regions show chaos terrain where the surface appears to have broken apart and refrozen in a jumbled mess. Scientists think the ice crust floats on the liquid ocean beneath, similar to ice flows on Earth's Arctic Ocean. Occasionally, the crust breaks, allowing water from below to well up and refreeze on the surface. This process might bring nutrients from the ocean up to where we can detect them, giving us clues about what is happening in the hidden water below. In 2013, the Hubble Space Telescope detected evidence of water plumes erupting from Europa's surface, shooting 125 miles into space before falling back down. These plumes might be water vapor escaping from the subsurface ocean through cracks in the ice. If so, future spacecraft could fly through these plumes and analyze their composition without even needing to land. But the big question is whether anything lives in Europa's ocean, and that question is not as far-fetched as it might sound. On Earth, life exists in the deep ocean, far from sunlight, near hydrothermal vents. These underwater volcanoes spew hot, mineral-rich water into the cold ocean. Entire ecosystems thrive around these vents, based not on photosynthesis, but on chemosynthesis. Bacteria use chemicals from the vents as an energy source, and other organisms feed on those bacteria. Life without sunlight, life powered by Earth's internal heat. Europa probably has hydrothermal vents on its ocean floor. The same tidal heating that keeps the water liquid would also drive volcanic activity on the ocean bottom. If Europa has vents like Earth's, it might also have ecosystems like Earth's. Simple microbes, at first perhaps, but maybe something more complex. Maybe something that has been evolving independently for billions of years, adapting to the eternal darkness, the high pressure, and the cold. We do not know. We cannot know until we send a probe to Europa, drill through the ice, and explore the ocean. But the possibility is tantalizing. Europa might be the first place beyond Earth where we find life. NASA is planning a mission called Europa Clipper, scheduled to launch in 2024 and arrive at Jupiter in 2030. The spacecraft will not land on Europa, but it will fly by the moon dozens of times, using radar to map the ice thickness, analyzing the surface composition, and searching for more evidence of water plumes. It will be the most detailed study of Europa ever conducted. But Europa is not alone. Another moon, orbiting Saturn, also hides a subsurface ocean, and this moon is even more surprising. Enceladus is tiny, only 310 miles in diameter, about as wide as the state of Arizona. It is one of Saturn's smaller moons, icy and reflective, shining brighter than any other object in the solar system because its surface is pure, fresh ice. For decades, scientists thought Enceladus was geologically dead, too small to retain internal heat, too far from the sun to have liquid water, just another frozen rock orbiting Saturn. But in 2005, the Cassini spacecraft flew by Enceladus and discovered something extraordinary. The moon was shooting geysers of water into space from its south polar region, not small trickles, massive plumes, fountains of ice particles and water vapor erupting from long cracks called tiger stripes, shooting hundreds of miles above the surface. This should not be possible. Enceladus is too small. It should have cooled off billions of years ago. But something is keeping its interior warm. Something is creating enough heat to maintain liquid water beneath the ice. The answer, again, is tidal heating. Enceladus has an eccentric orbit, and it is locked in an orbital resonance with another moon, Dione. The gravitational interactions squeeze and flex Enceladus, generating internal heat. Not as much as Europa, but enough to keep a subsurface ocean liquid. Cassini flew through Enceladus's plumes multiple times, analyzing their composition. The results were astounding. The plumes contain water, of course, but also salt, organic molecules, and molecular hydrogen. Molecular hydrogen is particularly interesting because it suggests hydrothermal activity on the ocean floor. Hydrogen is produced when hot water reacts with rock, the same process that happens at Earth's hydrothermal vents. Everything you need for life is present in Enceladus's ocean, liquid water, energy from hydrothermal vents, organic molecules, the right chemistry. If life exists there, it would be similar to life in Earth's deep oceans, thriving in complete darkness, powered by chemical energy instead of sunlight. And unlike Europa, where we would need to drill through miles of ice to reach the ocean, Enceladus brings its ocean to us. The geysers shoot ocean water directly into space, where spacecraft can sample it. Future missions could analyze those plumes in detail, searching for biosignatures, for any chemical hints that life might exist below. The discovery of Enceladus's ocean changed how scientists think about habitability. Enceladus was never considered a candidate for life. It is too far from the sun, too small, too cold, but it has everything life needs. And if Enceladus can harbor life, then maybe many other icy moons can too. Saturn alone has over 80 moons. Jupiter has 95. Uranus has 27. Neptune has 14. Some of these moons are tiny, just captured asteroids, but others are large, icy worlds that might hide oceans beneath their surfaces. Ganymede, the largest moon in the solar system, probably has an ocean. Callisto, another of Jupiter's large moons, might too. Titan, Saturn's largest moon, has liquid on its surface, though not water. Titan deserves special mention because it is one of the strangest worlds in the solar system. It is the only moon with a thick atmosphere, denser than Earth's. The surface pressure on Titan is about 1.5 times Earth's atmospheric pressure at sea level, and that atmosphere is mostly nitrogen, just like Earth's, though with methane instead of oxygen. Titan is so cold, averaging negative 290 degrees Fahrenheit, that water ice is as hard as rock. But methane and ethane, which are gases on Earth, are liquids on Titan, and Titan has lakes and seas of liquid methane and ethane, the only other world in the solar system known to have stable bodies of liquid on its surface. The Cassini mission detected dozens of lakes in Titan's polar regions and a few large seas. The largest, Kraken Mare, is bigger than the Caspian Sea on Earth. These are not water, they are hydrocarbons, the same chemicals that make up natural gas and gasoline, but they behave like water on Titan, forming clouds, falling as rain, filling rivers and lakes. Titan also has weather, methane rain, ethane fog, clouds drifting through the thick, hazy atmosphere. It even has seasons, though they are much longer than Earth's because Saturn takes 29.4 Earth years to orbit the Sun. In 2005, the Huygens probe, part of the Cassini mission, landed on Titan's surface. It sent back images of a landscape that looked eerily Earth-like, rounded pebbles, carved by flowing liquid, river channels, a shoreline, but everything was made of ice instead of rock, and the liquid was methane instead of water. Beneath Titan's surface, scientists think there is another ocean, this one made of water mixed with ammonia, kept liquid by internal heat and the antifreeze effect of the ammonia. So Titan has two layers of liquid, methane on the surface, water below. It is a layered world, complex and strange, unlike anywhere else we know. Could life exist on Titan? Not life like Earth's, which depends on liquid water, but perhaps a different kind of life. Life based on methane chemistry instead of water chemistry. Life that uses liquid hydrocarbons the way Earth life uses liquid water. This is speculative, highly uncertain, but not impossible. The universe might be more creative than we imagine. These icy moons, Europa and Enceladus, and Titan and others, represent some of the best places to search for life beyond Earth. They are more promising than Mars, which is cold and dry and has only traces of water. They are more accessible than exoplanets orbiting distant stars. They are right here in our solar system, waiting to be explored. And they remind us that life does not need Earth-like conditions to exist. It does not need sunlight. It does not need a warm surface. It just needs liquid water, or perhaps liquid something, and an energy source. The solar system might be full of hidden oceans, buried beneath ice, harboring ecosystems we have never imagined. These oceans have been there for billions of years, completely isolated from the rest of the universe. If life evolved there, it evolved independently. It would be a second Genesis, proof that life is not a unique accident that happened once on Earth, but a natural process that occurs whenever conditions are right. Finding life on Europa or Enceladus would be one of the most important discoveries in human history. It would answer the question we have been asking for millennia: are we alone? And the answer would be no. We are not alone. Life emerged at least twice in our solar system, and if it happened twice here, it probably happened countless times across the galaxy, across the universe. But even if we find nothing, Even if those oceans are sterile, the search itself is valuable. It teaches us about the limits of life, about what conditions are necessary, and what conditions are sufficient. It expands our understanding of what is possible. For now, those oceans remain hidden, silent, dark, waiting for us to reach them, waiting for us to dip a probe beneath the ice and see what 4 billion years of isolation has created. Sleep tonight, knowing that beneath the frozen surfaces of distant moons, vast oceans might harbor life, creatures that have never seen a star, ecosystems that evolved in eternal darkness, worlds within worlds, hidden in plain sight, circling gas giants, patiently waiting for the day we finally arrive to explore them. The universe is full of secrets, and some of those secrets swim in alien seas beneath ancient ice. Beyond the asteroid belt, beyond the rocky inner planets, the solar system changes. The worlds become enormous, made not of rock and metal, but of hydrogen and helium, the same elements that make up the sun. Planets so large that Earth could fit inside them dozens or hundreds of times. Planets with no solid surface, just endless layers of gas and liquid compressed by their own immense gravity. Planets where storms rage for centuries, driven by internal heat and rapid rotation, creating weather systems unlike anything we see on Earth. These are the gas giants: Jupiter, Saturn, Uranus, and Neptune, and they are among the most beautiful and violent objects in the solar system. Start with Jupiter, the king of planets, the largest world orbiting our sun. Jupiter has a mass 318 times greater than Earth. If you could somehow gather every other planet, moon, asteroid, and comet in the solar system and combine them into one object, Jupiter would still be more than twice as massive. It is enormous, incomprehensibly large, and it dominates the outer solar system with its gravity. But what makes Jupiter truly remarkable is not its size. It is the storm that has been raging on its surface for at least 190 years, possibly much longer. The Great Red Spot. There's a massive anticyclonic storm rotating counterclockwise in Jupiter's southern hemisphere. When astronomers first began detailed observations of Jupiter in the 1800s, the Great Red Spot was already there, already massive, already churning. No one knows how long it has existed. Some think it might be over 350 years old, possibly observed by early astronomers with primitive telescopes in the 1600s. The storm is huge. At its largest in the late 1800s, it was about 25,000 miles wide. That is more than 3 times the diameter of Earth. You could fit 3 Earths side by side inside the Great Red Spot, and they would still have room to spare. In recent decades, the storm has been shrinking. By 2020, it was about 10,000 miles across, still larger than Earth, but smaller than it used to be. Scientists are not entirely sure why it is shrinking. It might be losing energy, it might be a natural fluctuation, or it might eventually dissipate entirely, ending a storm that has lasted for centuries. But for now, the Great Red Spot persists, and studying it has taught us a lot about atmospheric dynamics on gas giant planets. Unlike Earth's hurricanes, which derive their energy from warm ocean water, the Great Red Spot is powered by Jupiter's internal heat. Jupiter radiates more energy than it receives from the Sun. The planet is still slowly contracting from its formation 4.6 billion years ago, and that contraction generates heat. Rising currents of warm gas meet descending currents of cooler gas, creating massive convection cells that drive Jupiter's weather. The Great Red Spot is an anticyclone, meaning it rotates in the opposite direction from cyclones, like hurricanes on Earth. Winds around the edge of the storm reach speeds of about 270 to 425 miles per hour. That is faster than any wind ever recorded on Earth, and those winds have been blowing for at least 190 years, possibly much longer, without slowing down significantly. Why does the storm last so long? On Earth, hurricanes dissipate when they hit land or move over cold water. But Jupiter has no land, no solid surface, just gas, all the way down, getting denser and hotter until eventually it transitions into liquid metallic hydrogen thousands of miles below the visible clouds. There is nothing to disrupt the storm, nothing to stop it except other atmospheric features. And Jupiter has many other storms, smaller white ovals, brown barges, and countless swirling vortices. Sometimes smaller storms merge with larger ones. Sometimes they pass by each other without interacting. The entire atmosphere is a chaotic, turbulent place with jet streams moving at different speeds at different latitudes, creating shear zones where storms can persist for decades or centuries. The Great Red Spot sits in one of these shear zones. Jet streams to its north and south move at different speeds, hemming in the storm, preventing it from drifting too far or dissipating too quickly. The storm feeds on the energy from these jet streams, drawing in smaller vortices and absorbing their momentum. It is a self-sustaining system as long as the surrounding atmosphere continues to provide energy. From a distance, the Great Red Spot looks serene, almost peaceful, a beautiful reddish-brown oval in Jupiter's banded atmosphere. But up close, it would be terrifying. Wind speeds that would tear apart any structure humans could build, pressure gradients that would crush anything trying to enter, lightning bolts thousands of times more powerful than Earth's, thunder that would be deafening if there were anyone to hear it. And it never stops. Day after day, year after year, century after century, the storm churns on, completely indifferent to whether anyone is watching, completely unconcerned with whether it will last another year or another 1,000 years. It just exists, doing what storms do, following the laws of physics, transforming Jupiter's internal heat into motion. Now travel outward to Saturn, smaller than Jupiter, but still enormous, 95 times the mass of Earth. Saturn is famous for its rings, but its atmosphere is just as fascinating. Saturn has a storm unlike any other in the solar system. At its north pole, winds form a perfectly hexagonal pattern, a six-sided jet stream, each side about 8,600 miles long. The hexagon is so large you could fit nearly 2 Earths inside it, and it has been there for decades, possibly much longer. The Voyager spacecraft first observed the hexagon in 1981. The Cassini spacecraft studied it in detail from 2004 to 2017, and throughout that entire time, the hexagon remained stable. Same shape, same size, same location. A geometric pattern in chaotic turbulence, persisting without any obvious explanation. Scientists think the hexagon is created by jet stream interactions. Winds at different latitudes, moving at different speeds, can create standing wave patterns. Under certain conditions, Those waves can lock into stable polygonal shapes. Computer simulations have reproduced hexagonal patterns in rotating fluids, suggesting that Saturn's hexagon is a natural consequence of atmospheric dynamics. But seeing it in nature at such an enormous scale is still astonishing. Inside the hexagon sits Saturn's north polar vortex, a massive cyclone rotating at the pole. The vortex is about 1,250 miles across, roughly the size of Earth, and unlike Jupiter's storms, which are mostly horizontal, Saturn's polar vortex extends deep into the atmosphere, possibly reaching hundreds of miles down. The vortex has an eye, similar to a hurricane's eye on Earth, but Saturn's eye is about 1,250 miles across, 50 times larger than a typical hurricane eye. Winds around the eye reach 330 miles per hour, and the entire structure rotates once every 10.7 hours, matching Saturn's rotation period. At Saturn's south pole, there is also a vortex, though without the hexagonal pattern. The South Pole vortex was studied extensively by Cassini before the spacecraft ended its mission by diving into Saturn's atmosphere in 2017. The vortex showed similar characteristics to the North Pole storm, with a large eye and high wind speeds, but it had a more circular shape. Saturn, like Jupiter, radiates more energy than it receives from the sun. Internal heat drives atmospheric convection, creating the storms and jet streams we observe. Saturn's rapid rotation, just 10.7 hours for a complete spin, also contributes to the atmospheric dynamics. The fast rotation creates strong Coriolis forces, influencing how storms develop and persist. And throughout Saturn's atmosphere, smaller storms come and go, and for a few decades, a massive storm system erupts near Saturn's equator, wrapping around the entire planet in what astronomers call a great white spot. These storms last for months, dissipating slowly as they spread across the globe. The most recent one occurred in 2010 to 2011, visible even from Earth through amateur telescopes. But the strangest weather in the solar system might be on Neptune, the farthest planet from the Sun, so distant that it receives only about 0.1% of the sunlight that Earth receives. You would think Neptune would be quiet, calm, geologically dead. Instead, Neptune has the fastest winds in the solar system. Wind speeds on Neptune reach up to 1,200 miles per hour, faster than the speed of sound on Earth, faster than any jet stream on any other planet. These supersonic winds race around the planet in bands, creating massive storm systems that appear and disappear over years or decades. When Voyager 2 flew by Neptune in 1989, it observed a massive storm called the Great Dark Spot, similar in size and behavior to Jupiter's Great Red Spot. The storm was about 8,000 miles across, roughly the size of Earth, and it rotated counterclockwise in Neptune's southern hemisphere. But when the Hubble Space Telescope observed Neptune a few years later, the Great Dark Spot was gone. It had disappeared completely. In its place, a different dark spot had appeared in the northern hemisphere. Neptune's storms are not permanent like Jupiter's. They form, persist for a few years or decades, then vanish, replaced by new storms elsewhere on the planet. Why does Neptune have such extreme weather? The planet is so far from the Sun that solar heating is negligible. But like Jupiter and Saturn, Neptune radiates more energy than it receives. In fact, Neptune radiates about 2.6 times more energy than it absorbs from sunlight. That internal heat, combined with Neptune's rapid 16-hour rotation, drives the violent atmospheric dynamics. But there is still a mystery. Neptune radiates less internal heat than Jupiter or Saturn, yet its winds are faster. Scientists do not fully understand why. It might have to do with the composition of Neptune's atmosphere, which contains more methane and other compounds than Jupiter's hydrogen helium mix. Or it might be related to convection patterns deep in the planet's interior. We do not know. Neptune keeps its secrets. Uranus, the other ice giant, is quieter. Its atmosphere appears relatively bland, with few visible storms. This might be because Uranus is tipped on its side, with an axial tilt of 98 degrees. One pole faces the sun for 42 years, then the other pole faces the sun for 42 years. This unusual orientation might affect atmospheric circulation, creating different patterns than on the other gas giants. But even Uranus has occasional storm activity. Recent observations have shown increasing numbers of clouds and storms in Uranus's atmosphere, possibly related to seasonal changes as the planet approaches its equinox. All these gas giants share a common feature. They have no solid surface to stop their storms, no mountains to break up jet streams, no continents to absorb energy. The storms just persist, sometimes for centuries, driven by internal heat and rapid rotation, following the laws of fluid dynamics on an enormous scale. And all these storms happen in silence. No sound travels through the vacuum of space. No thunder reaches our ears. The most violent weather in the solar system occurs without making a noise, just massive vortices of gas churning through atmospheres thousands of miles deep, seen only by our telescopes and spacecraft, recorded only in images and data. From Earth, even through large telescopes, the gas giants look peaceful. Jupiter's bands of clouds, Saturn's rings, Neptune's blue haze. They appear calm, distant, beautiful, but those appearances hide incredible violence, winds that would destroy anything in their path, pressure gradients that would crush steel, lightning bolts that make Earth's storms look like gentle rain showers. And yet, there is something calming about knowing these storms exist, something reassuring. They remind us that the universe is active, that planets are not static, dead objects, but dynamic systems constantly changing, constantly moving, constantly evolving, even on worlds with no solid surface, with no life, with no one to witness them. Storms rage on. The universe does not need an audience. It performs regardless. Tonight, as you fall asleep, Jupiter's great red spot continues spinning. Saturn's hexagon maintains its shape. Neptune's winds race across the planet at supersonic speeds, and all of it happens without anyone watching, without anyone caring. The storms persist because that is what storms do. They follow the physics. They transform energy into motion. They exist, and in a strange way, that persistence is comforting. The universe is not fragile. It does not need protecting. It just continues, storm after storm, century after century, indifferent to observers, indifferent to time, just doing what it has always done. Rest now, knowing that out there, in the outer solar system, massive storms rage on. They have been raging since long before you were born. They will continue long after you are gone, and they ask nothing of you except perhaps a moment of wonder, a brief appreciation for the power and beauty of nature operating on scales beyond human comprehension. Of all the objects in the solar system, few are as instantly recognizable or as hauntingly beautiful as Saturn's rings. Even through a small telescope, they are unmistakable, a bright jewel surrounded by delicate bands of light, suspended in the darkness like nothing else we have ever seen. They look permanent, eternal, as if they have always been there and always will be. But they are fragile, temporary, younger than the dinosaurs, and they are slowly disappearing. Let me tell you what Saturn's rings really are. From a distance, they look solid, smooth bands of white and gold circling the planet, but up close, the illusion shatters. The rings are not solid at all. They are made of billions upon billions of individual particles, each one orbiting Saturn independently. Ice particles, mostly, ranging in size from grains of sand to chunks the size of houses. Some pieces are pure water ice, reflecting sunlight brilliantly. Others are coated with dust or organic compounds, giving the rings subtle color variations. Each particle follows its own elliptical orbit around Saturn. Closer particles orbit faster, farther particles orbit slower. This is the same principle that governs planetary orbits around the Sun, just on a much smaller scale. The result is a disk of orbiting material that appears from a distance to be a solid structure, but is really just countless individual objects moving in lockstep. And that disk is incredibly thin. The rings span about 175,000 miles from inner edge to outer edge, but in most places they are only about 30 feet thick. 30 feet. If you scaled the rings down to the size of a football field, they would be thinner than a sheet of paper. You could pass through them in a spacecraft in a few seconds, barely noticing the transition, except for the pinging of ice particles against your hull. The thinness is remarkable. It means the ring particles have very flat, very circular orbits. If their orbits were tilted even slightly, the rings would be much thicker, but gravitational interactions between particles and tidal forces from Saturn itself have flattened everything into an incredibly precise plane. The rings are divided into several major sections, labeled alphabetically in the order they were discovered, not their distance from Saturn. The main rings, from innermost to outermost, are the D ring, C ring, B ring, A ring, F ring, D ring, and E ring. Each ring has different properties, different particle densities, different compositions. The B ring is the brightest and most opaque. It reflects almost 60% of the sunlight that hits it, making it visible even from Earth through small telescopes. The particles in the B ring are densely packed. Relatively speaking, they still have plenty of space between them, but they are close enough to collide occasionally, grinding down into smaller pieces over time. The A ring is separated from the B ring by the Cassini division, a 920-mile gap that appears dark from Earth. Early astronomers thought the Cassini division was empty, but spacecraft observations revealed it contains sparse ring material. The gap exists because particles orbiting in that region are in an orbital resonance with Mimas, one of Saturn's moons. Mimas orbits Saturn in almost exactly twice the time it would take a particle in the Cassini division to orbit. This 2-to-1 resonance creates gravitational tugs that destabilize particle orbits, clearing out the gap over millions of years. The Pfeff ring is the strangest. Narrow, twisted, braided. It lies just outside the Aft ring and is shepherded by two small moons, Prometheus and Pandora. These shepherd moons orbit on either side of the Aft ring, and their gravity keeps the ring particles confined to a narrow band. But the shepherd moons also create waves and kinks in the ring as they pass. The Aft ring is constantly changing shape, sometimes showing knots and clumps, sometimes smoothing out. It is the most dynamic structure in Saturn's ring system. Beyond the main rings, the E ring extends far out into space, fed by water geysers from Enceladus. The E ring is incredibly diffuse, made of tiny ice particles that reflect sunlight but are spread out over a huge volume. It is barely visible, more of a faint haze than a solid structure. Where did Saturn's rings come from? That is one of the most debated questions in planetary science. For a long time, scientists thought the rings were as old as Saturn itself, formed 4.6 billion years ago from the same disk of material that created the planet and its moons. But recent observations suggest something different. The rings might be much younger, perhaps only 100 to 200 million years old. The evidence comes from several sources. The rings are very bright, very clean ice. If they had been around for billions of years, they should be darker, dirtier, coated with micrometeorite dust from space. But they are not. They look young, fresh, recently formed. The Cassini spacecraft, during its final orbits, measured Saturn's gravitational field with incredible precision. Those measurements allowed scientists to estimate the mass of the rings, and the rings turned out to be less massive than expected. If they were ancient, they should contain more material. The low mass suggests the rings are relatively young and possibly shrinking. So if the rings are young, how did they form? The most likely explanation is that a moon or large comet wandered too close to Saturn and crossed the Roche limit, the distance at which tidal forces from the planet become stronger than the object's self-gravity. Inside the Roche limit, tidal forces rip objects apart. The disrupted moon or comet would have broken into countless pieces, and those pieces would have spread out into the ring structure we see today. This means the rings are temporary. They were not there when dinosaurs ruled Earth. They will not be there in another few 100 million years. We are living during the brief window when Saturn has rings, and that is an incredible stroke of luck. But the rings are not just sitting there, static and unchanging. They are evolving. They are dying. Saturn has a magnetic field that interacts with charged particles in the rings. This interaction creates drag, pulling ring particles gradually inward. Scientists call this ring rain. Ice particles pulled by gravity and magnetic forces fall into Saturn's atmosphere, vaporizing as they descend. Estimates suggest Saturn loses between 925 and 6,000 pounds of ring material every second. That might not sound like much for such a massive structure, but over millions of years it adds up. At the current rate, the rings might only last another 100 million years, maybe less. Eventually, they will all fall into Saturn, and the planet will be a simple sphere, unadorned, like Jupiter or Neptune. The iconic feature that makes Saturn instantly recognizable will be gone. And when that happens, there will be no one to remember that Saturn once had rings, no one to pass down the story. The universe will have erased one of its most beautiful creations, and the only evidence will be faint traces in Saturn's atmosphere, chemical signatures of the ice that fell like rain over eons. But for now, the rings persist, and they are stunningly beautiful. Galileo was the first to see them. In 1610, though his primitive telescope could not resolve them clearly, he thought Saturn had ears, two large protrusions on either side of the planet. Only later, as telescopes improved, did astronomers realize the ears were actually rings. In the centuries since, Saturn's rings have inspired countless poets, artists, and scientists. They represent something perfect, something elegant, and natural structure of such geometric precision that it seems almost designed, but no one designed it. The rings exist because of physics, because of gravity and orbital mechanics and tidal forces. They are beautiful by accident. When the Cassini spacecraft orbited Saturn from 2004 to 2017, it sent back images of the rings in breathtaking detail. Waves rippling through the ring particles caused by gravitational interactions with moons, propeller-shaped disturbances created by small embedded moonlets, shadows cast by the rings onto Saturn's cloud tops, the rings backlit by the sun, revealing delicate structure invisible from Earth. One of the most iconic images from Cassini is called The Day the Earth Smiled. Taken in 2013, it shows Saturn with its rings fully illuminated, and there in the background, a tiny pale blue dot, Earth, barely visible, a reminder that we are part of this system, however distant we might feel. The rings look different depending on Saturn's position in its orbit. Saturn is tilted 26.7 degrees, similar to Earth's tilt. As Saturn orbits the Sun over its 29.4-year period, the rings appear to open and close from our perspective. When Saturn is at certain points in its orbit, we see the rings edge on. They become almost invisible, just a thin line cutting across the planet. When Saturn is at other points, the rings are wide open, showing their full glory. Every 14.7 years, Earth crosses the plane of Saturn's rings, an event called ring plane crossing. During these crossings, the rings vanish from view for a few weeks or months, too thin to see. But it is also the best time to discover new moons. When the bright rings disappear, faint moons that are usually lost in the glare become visible. Several of Saturn's smaller moons were discovered during ring plane crossings. The rings cast shadows on Saturn, dark bands across the cloud tops, and Saturn casts a shadow on the rings, creating a region where sunlight cannot reach. In that shadow, the temperature drops, and some scientists think that might affect the behavior of the ring particles, though the effects are subtle. There is something deeply calming about Saturn's rings. Maybe it is the symmetry, the perfect circular bands, the way they catch sunlight and reflect it back into space. Or maybe it is the knowledge that they are temporary, that we are lucky enough to live during the brief moment when they exist. Most planets do not have rings like Saturn's. Jupiter has faint rings, barely visible. Uranus and Neptune have narrow, dark rings, but none of them compare to Saturn. None have that combination of brightness, size, and complexity. Saturn's rings are unique, irreplaceable, and they are slowly fading away. In a few 100 million years, intelligent beings might look at Saturn through their telescopes and wonder why we were so fascinated by a plain ball of gas. They will not understand that once, long ago, that plain ball was adorned with the most beautiful structure in the solar system. They will not know what they missed, but we know. We live during Saturn's moment of glory. We can see the rings. We can study them. We can marvel at them. and we can appreciate how rare and precious they are. Tonight, as you fall asleep, Saturn continues its slow orbit around the Sun. The rings continue their gradual spiral inward. Ice particles continue falling into the planet's atmosphere like silent rain, and none of it matters to the universe. The rings do not know they are beautiful. They do not know they are temporary. They just exist, following the laws of physics, unaware of their own magnificence. But we are aware. And that awareness, that ability to see beauty in something as simple as orbiting ice particles, that is what makes us human. We find meaning in the meaningless. We see art in physics. We appreciate the temporary nature of all things and love them more because they do not last forever. Saturn's rings will not last forever, but for now, for this brief cosmic moment, they are here, elegant, perfect, slowly disappearing, a reminder that even the most beautiful things in the universe are transient. Rest now beneath the same stars that shine on Saturn's rings. Tomorrow they will still be there, still orbiting, still reflecting sunlight, still being the most beautiful accident in the solar system, but not forever, just for now. And now is enough. We think of the solar system as ending somewhere around Neptune, 8 planets, countless moons, and then nothing. Empty space stretching out to the nearest star. But that is not how it actually works. The solar system extends far beyond Neptune, much farther than most people realize, and out there, in the cold darkness beyond the familiar planets, billions of icy objects orbit the Sun in two vast reservoirs that mark the true boundaries of our cosmic neighborhood. These are the Kuiper Belt and the Oort cloud, and they are where comets come from. The Kuiper Belt begins just beyond Neptune's orbit at about 30 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So the Kuiper Belt starts at about 2.8 billion miles from the Sun and extends out to roughly 50 astronomical units, about 4.6 billion miles. That region, from 30 to 50 AU, contains millions of icy objects, maybe billions. We cannot count them all because most are too small and too far away to detect. But we have discovered thousands of them, and we are finding more every year. These objects are leftovers from the formation of the solar system. When the planets were coalescing from the protoplanetary disk 4.6 billion years ago, the region beyond Neptune never accumulated enough material to form a large planet. The objects there just stayed as they were, frozen in time, orbiting the Sun in nearly the same configuration they had 4 billion years ago. This makes the Kuiper Belt incredibly valuable for understanding the early solar system. The objects there have not changed much. They have not been heated by the Sun. They have not been altered by geological processes. They are pristine samples of the material that existed when the solar system was young. Studying them is like reading a history book written in ice. The largest known Kuiper Belt object is Pluto, once considered the ninth planet, now classified as a dwarf planet after the discovery of other similarly sized objects in the same region. Pluto orbits at an average distance of about 39.5 AU, taking 248 Earth years to complete one orbit. It is small, only about 1,473 miles in diameter, smaller than Earth's moon, and it is incredibly cold, with surface temperatures around negative 375 degrees Fahrenheit. But Pluto is not alone. It has at least 5 moons, the largest being Charon, which is about half Pluto's diameter. Pluto and Charon orbit each other so closely that they are sometimes called a binary system rather than a planet and moon. They are tidally locked, always showing the same face to each other, spinning in perfect synchronization. When the New Horizons spacecraft flew by Pluto in 2015, it revealed a world far more complex than anyone expected. Mountains made of water ice, reaching 11,000 feet high, vast plains of nitrogen ice, smooth and crater free, indicating recent geological activity, a thin atmosphere that extends far into space, slowly escaping into the void, and a large heart shaped region called Tumba Regio, where nitrogen, methane, and carbon monoxide ices cover the surface. Pluto should be geologically dead. It is too small to retain much internal heat, too far from the sun to receive significant solar energy, but something is keeping it active. Perhaps tidal heating from Chiron, perhaps radioactive decay in the core, or perhaps something we do not yet understand. Pluto keeps its secrets. Beyond Pluto, other dwarf planets orbit in the Kuiper belt. Eris, slightly more massive than Pluto, orbits at about 68 AU on average, but has a highly elliptical orbit that takes it as far as 97 AU from the Sun. Maycapes Haumea and others, each one a small icy world, barely warm enough to have surfaces that are not completely frozen solid. These objects are the source of short period comets, comets that orbit the Sun in less than 200 years. Sometimes gravitational interactions with Neptune perturb a Kuiper Belt object's orbit, sending it plunging toward the inner solar system. As it approaches the Sun, the ice begins to vaporize, creating the spectacular tails that make comets visible from Earth. Halley's Comet is one of the most famous short period comets, taking about 76 years to orbit the Sun. It has been observed by humans for more than 2,000 years, appearing in historical records from ancient China, Babylon, and medieval Europe. It came from the Kuiper Belt originally, though its orbit has been altered by multiple passes through the inner solar system. But the Kuiper Belt is just the beginning. Beyond it, much farther out, lies the Oort cloud. The Oort cloud has never been directly observed. We know it exists because of the comets that come from it, but we have never sent a spacecraft there. We have never seen it with telescopes. It is too far away, too sparse, too faint, but the mathematics and the observations of long period comets tell us it must be there. The Oort cloud is a spherical shell of icy objects surrounding the entire solar system. It begins at about 2000 AU from the Sun and extends out to perhaps 100,000 AU, maybe farther. We do not know the exact outer boundary. At its farthest extent, the Oort cloud reaches about halfway to the nearest star. To put those distances in perspective, light takes about 8 minutes to travel from the Sun to Earth. Light takes about 4 hours to reach Neptune, but light takes more than a year to reach the inner edge of the Oort cloud, and it takes about a year and a half to reach the outer edge. The Oort cloud occupies a truly vast volume of space. Estimates suggest the Oort cloud contains trillions of objects, not millions, not billions, trillions. Most are small, just a few miles across, made of water ice, methane ice, and other frozen volatiles. They orbit the Sun so slowly that a single orbit takes millions of years. An object at the outer edge of the Oort cloud 100,000 AU from the Sun would take roughly 6 million years to complete one orbit. 6 million years. Let that settle in. When that object last passed through its current position, early humans were just beginning to diverge from other apes, and it will not return to this position for another 6 million years, long after our species has either evolved into something unrecognizable or gone extinct. These objects have been out there, orbiting in the darkness, since the solar system formed. They have never been close to the sun. They have never experienced warmth. They just drift through the void, silently, patiently, taking millions of years to complete each lap around a star they can barely see. Occasionally, a passing star or a gravitational perturbation from the galaxy itself nudges an Oort cloud object, altering its orbit just enough to send it falling inward toward the sun. These objects become long period comets, comets with orbital periods longer than 200 years. Some take thousands of years to orbit once. Some have such elongated orbits that they only pass through the inner solar system once before being flung back out, never to return. When one of these comets approaches the sun for the first time, it is called a pristine comet. It has never been heated before, never vaporized its ice, and as it warms, it can become incredibly bright, developing a coma and tail that stretch for millions of miles. These are the great comets that appear suddenly in the night sky, visible even in daylight, spectacular and unexpected. The Oort cloud formed from material ejected by the giant planets during the early solar system's chaotic period, when Jupiter, Saturn, Uranus, and Neptune were migrating to their current orbits. Their gravity flung countless small objects outward. Some were ejected from the solar system entirely, but others settled into distant orbits, forming the Oort cloud. In a sense, the Oort cloud is the edge of the solar system. Objects there still orbit the sun, still feel its gravity, but they are so far away that they barely experience its warmth or light. The sun appears from the Oort cloud as just another star, brighter than the others, but not by much. And yet those objects are still part of our system. They were born here. They have orbited the sun for 4.5 billion years. They will continue orbiting for billions more unless something disturbs them. The Oort cloud might also contain rogue planets, objects large enough to be considered planets, but never captured into close orbits around the sun. These hypothetical worlds, sometimes called Planet 9 or Planet X, would orbit so far out and so slowly that we have not detected them yet. Some scientists think there might be a planet several times the mass of Earth orbiting in the outer solar system, based on the way certain Kuiper Belt objects' orbits are clustered, but no one has found it yet. If it exists, it is out there in the darkness, invisible, waiting. Voyager 1 and Voyager 2, the two spacecraft launched in 1977 to explore the outer planets, are now traveling through interstellar space. They have crossed the heliopause, the boundary where the solar wind meets the interstellar medium, but they have not left the solar system. They are still inside the Oort cloud, and they will be for another 30,000 years. Even traveling at about 38,000 miles per hour, Voyager 1 will take roughly 300 centuries to exit the Oort cloud. That is longer than recorded human history. That is longer than agriculture has existed. By the time Voyager leaves the Oort cloud, humanity will likely be extinct or evolved into something unrecognizable or spread across the galaxy. The spacecraft will just keep going, silently, carrying its golden record with sounds and images from Earth, a message in a bottle flung into the cosmic ocean. And after it leaves the Oort cloud, Voyager will enter true interstellar space, the region between stars, no longer orbiting the sun, no longer part of any solar system, just drifting through the galaxy, one tiny artifact from a brief period when a species on a small planet built machines and sent them into the void. But for now, Voyager is still inside the sun's gravitational influence, still part of the solar system, even though it is farther from the sun than any human made object has ever been. The solar system is larger than we imagine, larger than diagrams suggest, larger than models show. It extends for light years in every direction, a vast sphere of icy objects orbiting a star that formed 4.5 billion years ago from a collapsing cloud of gas and dust. We live in the inner solar system, close to the sun, where warmth and light make life possible. But the outer solar system is where most of the volume exists. The Kuiper Belt and Oort cloud are not minor features. They are the majority of the solar system's extent. We just happen to live in the tiny warm center. And out there, in the cold darkness, trillions of objects orbit, silently, patiently, taking millions of years per orbit, never rushing, never hurrying, just following their paths through space as they have for longer than complex life has existed on Earth. There is something humbling about that, something that puts our existence into perspective. We have been here for a few 100,000 years. We have built civilizations for a few thousand years. But those icy objects have been orbiting for 4.5 billion years. They were there before Earth's oceans formed. They were there before life began. And they will be there long after our species is gone, still orbiting, still patient, still indifferent to whether anyone is watching. The Kuiper Belt and Oort cloud are the forgotten parts of the solar system, the regions we never see, the places we will likely never visit, but they are part of our home, part of the system that gave birth to Earth, and they remind us that even in our own neighborhood, there are vast regions we have not explored, objects we have not discovered, mysteries we have not solved. Tonight, as you lie in your bed, know that beyond Neptune, beyond Pluto, beyond the farthest objects we have named, trillions more orbit in the darkness. They do not know you exist. They do not care. They just keep orbiting, slowly, endlessly, following paths laid down billions of years ago. The solar system is larger than you think, and even its edges, its farthest reaches, are still within the sun's domain. We have not left the solar system. We are still home, just in the warm, bright center of a system that extends for light years in every direction. Rest now knowing that the boundaries of home are farther than you ever imagined. And out there, in the dark, ancient ice, waits patiently, orbiting the same star that warms your face on a summer day, connected to you by gravity across unimaginable distance. Now we leave the solar system behind. We leave the sun's gravitational influence. We leave the Oort cloud and enter true interstellar space, the region between stars, the vast emptiness that separates one stellar system from another. And here, in this darkness, we find something unexpected. The space between stars is not completely empty. It should be. Space is mostly vacuum. We have talked about this before. But even in the great voids between stellar systems, there is something, a thin gas, a sparse collection of atoms and molecules floating in the darkness. Astronomers call it the interstellar medium, and it is one of the most important components of the galaxy. The density is incredibly low. On average, there is about one atom per cubic centimeter of space, sometimes more, sometimes less, but roughly one atom per thimbleful of volume. That is far, far less dense than the best vacuum we can create in laboratories on Earth. It is almost nothing, but it is not quite nothing. And in a galaxy containing trillions upon trillions of cubic centimeters of space, even that thin gas adds up. The total mass of the interstellar medium in the Milky Way is roughly equal to about 10 billion times the mass of the Sun. That is a significant fraction of the galaxy's visible matter, scattered across the space between stars, rather than concentrated in stellar cores. The interstellar medium is not uniform. Some regions are denser than others, some are hotter, some are colder, and these variations tell stories about what has happened in the galaxy over billions of years. Start with the cold regions, molecular clouds. Astronomers call them, these are the densest parts of the interstellar medium, with densities reaching a few hundred or even a few thousand atoms per cubic centimeter. That is still incredibly sparse compared to Earth's atmosphere, which contains about 10 to the 19th power molecules per cubic centimeter. But in the context of space, these clouds are thick. Molecular clouds are cold, very cold. Temperatures average around 10 to 20 Kelvin, just a few degrees above absolute zero. And those temperatures, atoms combine into molecules. Hydrogen atoms pair up to form H2, molecular hydrogen. Carbon and oxygen form carbon monoxide. Nitrogen pairs with hydrogen to create ammonia. Water forms, though it remains frozen as ice crystals coating dust grains. These clouds are the stellar nurseries, the places where new stars form. Gravity slowly pulls the gas together, compressing it over millions of years. As the cloud collapses, it fragments into smaller clumps. Each clump continues collapsing, heating up from the compression. Eventually, the core becomes hot enough and dense enough for nuclear fusion to ignite. A star is born. The process is slow, patient. A molecular cloud might take 10 million years to collapse and form stars. But once fusion begins, the new star illuminates the surrounding gas, creating beautiful nebulae visible from Earth. The Orion Nebula, one of the brightest nebulae in our sky, is a stellar nursery. Stars are forming there right now, even as you lie in your bed. New suns are igniting in that cloud, beginning their billion-year journeys through the galaxy. But molecular clouds are dark. They absorb light. If you tried to shine a flashlight through a molecular cloud, the light would be absorbed by the dust grains suspended in the gas. From the outside, molecular clouds appear as dark patches against the background stars, regions where the starlight is blocked. The Coalsack Nebula in the southern sky is one such dark cloud, a black smudge visible to the naked eye, blocking the light from more distant stars. Then there are the warm regions, the intercloud medium. Temperatures here average around 8,000 Kelvin, hot enough that atoms remain ionized. Electrons are stripped from atoms, creating a plasma. The density is lower than in molecular clouds, typically less than one atom per cubic centimeter. This gas fills the spaces between clouds, a thin, hot medium permeating the galaxy. The warm intercloud gas comes from several sources. Some is material blown out from dying stars. Red giants lose their outer layers through stellar winds, gently releasing gas into space. Supernovae eject their outer layers violently, scattering heavy elements across light years of space. Young, massive stars emit intense stellar winds that push gas away from them. All of this material ends up in the interstellar medium, mixing with the primordial hydrogen and helium left over from the Big Bang. Then there are the hot regions, supernova remnants, and superbles. When a star explodes as a supernova, it sends a shock wave through the surrounding gas. That shock wave heats the gas to millions of Kelvin. The hot gas glows in X rays, creating expanding bubbles of superhot plasma that can be hundreds of light years across. These superbles are not permanent. They expand for hundreds of thousands or millions of years, then gradually cool and dissipate, merging back into the general interstellar medium. But while they exist, they dominate the local environment, pushing gas around, compressing molecular clouds, sometimes triggering new star formation in the compressed regions. And throughout all of this, there are cosmic rays, high energy particles, mostly protons, traveling at nearly the speed of light. Cosmic rays originate from supernovae, from pulsars, from black holes, and from sources outside our galaxy. They pass through the interstellar medium constantly, colliding with atoms, ionizing gas, creating secondary particles. Cosmic rays are dangerous. On Earth, we are protected by the atmosphere and the magnetosphere. But in interstellar space, there is no protection. A human traveling between stars would be constantly bombarded by cosmic rays, receiving radiation doses far beyond safe levels. Spacecraft shielding can reduce the exposure, but it cannot eliminate it. Interstellar travel for biological organisms is hazardous. Even spacecraft are affected. The Voyager probes, now traveling through interstellar space, detect cosmic rays continuously. The rate increases when they cross into regions with higher cosmic ray flux, providing clues about the structure of the interstellar medium and the boundary between the solar wind and the galaxy. The interstellar medium also contains dust, not dust like you find on furniture. Interstellar dust grains are microscopic, typically less than 1 micrometer across, made of carbon compounds, silicates, and ices. They form in the atmospheres of dying stars and in the ejecta from supernovae. Then they drift through space, coalescing into larger grains over time. These dust grains play a crucial role in star formation. They provide surfaces where atoms can stick together and form molecules. Without dust grains, molecular clouds would have far fewer molecules, and star formation would be less efficient. The dust also absorbs and scatters light, creating the dark clouds and the reddening of starlight we observe. But dust grains are more than just facilitators of chemistry. They are time capsules. Some grains found in meteorites are older than the solar system. They formed around stars that lived and died before the sun was born. These presolar grains carry isotopic signatures that reveal what kind of star they came from. By studying them, scientists learn about the nucleosynthesis processes in ancient stars, about the conditions in the early galaxy, about the history written in microscopic particles. The interstellar medium is constantly churning. Gas flows from one region to another. Stars form from dense clouds, then explode and return material to space. The cycle repeats endlessly. Over billions of years, the same atoms might become part of many different stars, many different planets, many different structures. The Sun formed from a molecular cloud 4.6 billion years ago. That cloud contained gas from earlier generations of stars, and when the Sun eventually dies, it will return its material to the interstellar medium, where it will mix with gas from other dying stars and perhaps become part of future stellar systems. Nothing is wasted. Everything is recycled. The interstellar medium is the galaxy's reservoir, storing material between stellar generations, keeping it available for the next round of star formation. But the interstellar medium is not evenly distributed across the galaxy. The galactic disk, where most stars reside, has more gas than the galactic halo. The spiral arms, where star formation is active, have more molecular clouds than the regions between arms. And near the galactic center, the density increases dramatically. The environment there is chaotic, with intense radiation, powerful magnetic fields, and supermassive black holes influencing the gas dynamics. Our solar system, fortunately, resides in a relatively calm region. The local bubble, astronomers call it, a region about 300 light years across, where the gas density is lower than average. This bubble was probably created by multiple supernovae that exploded in the region over the past few million years. The explosions swept gas out of the area, creating a cavity of low density hot gas. The Sun is currently traveling through a small cloud within the local bubble called the local interstellar cloud. This cloud has slightly higher density than the surrounding medium, perhaps zero point 0.3 atoms per cubic centimeter. It is a small warm cloud, not a molecular cloud, just a minor fluctuation in the already sparse interstellar gas. The solar system has been inside the local interstellar cloud for the past 44,000 years and will exit it in another 10,000 to 20,000 years. Then we will enter a different region of the local bubble with slightly different properties. The transition will not be dramatic. We will not notice it on Earth, but the heliosphere, the bubble created by the solar wind, might change shape slightly. The density of neutral atoms entering the solar system might increase or decrease. These are the subtle changes that happen as the solar system drifts through the galaxy. We move through different regions of the interstellar medium, each with its own density, temperature, and composition. The Sun's orbit around the galactic center takes 225 million years, and during that time, we pass through spiral arms, through dense clouds, through sparse regions. The environment changes constantly on cosmic timescales, and in all of this, one fact remains. The interstellar medium is mostly empty. Even the densest molecular clouds are far less dense than the air you breathe. But that emptiness is not sterile. It is not dead. It is full of potential, full of atoms waiting to become part of something, full of molecules drifting through the dark, full of dust grains carrying memories of ancient stars. The space between stars is where the galaxy stores its building materials, where it keeps the raw ingredients for the next generation of stars and planets, and perhaps life. The interstellar medium is not the absence of matter, it is the presence of possibility. Right now, light from distant stars is passing through the interstellar medium, traveling for centuries or millennia, scattering off dust grains, being absorbed and re-emitted, slowly making its way to your eyes. When you look at the night sky, you are not just seeing stars, you are seeing light that has journeyed through the thin gas between stellar systems, carrying information about what it encountered along the way. And right now, atoms in the interstellar medium near our solar system are drifting slowly through space. Some will eventually be captured by the solar wind and drawn into the heliosphere. Some will remain in interstellar space for billions of years. And some might, in the distant future, become part of a new solar system, a new planet, a new living thing that wonders about the universe just as you do now. The interstellar medium connects us to the rest of the galaxy. It is the fabric that holds stellar systems together, not through direct contact, but through a shared medium. Every star in the Milky Way is immersed in this gas. Every star adds material to it. Every star draws material from it. We are not isolated islands. We are nodes in a vast network, connected by the thin gas that fills the space between. Tonight, as you fall asleep, remember that even in the emptiest regions of space, something exists. Atoms float in the darkness. Molecules form and break apart. Cosmic rays streak past at nearly light speed. Dust grains drift for eons. The universe is never truly empty. It is always full of motion, always changing, always preparing for what comes next. The interstellar medium is patient. It does not rush. It takes millions of years to form stars. It takes billions of years to recycle material through multiple stellar generations, but it never stops. The process continues, has continued for 13 billion years, will continue for billions more. Rest now in the knowledge that you are made of atoms that once floated in the interstellar medium. Your carbon, your oxygen, your nitrogen, all of it drifted through the space between stars before becoming part of the molecular cloud that formed the sun. You are not separate from the galaxy. You are part of it, made from it, connected to it through the thin gas that fills the darkness. The space between stars is not empty. It is full of history, full of potential, full of the materials that make everything, including you, sleep well in that knowledge. Everything I have told you tonight about the universe, all the stars and planets and galaxies and cosmic structures, all of it represents only a tiny fraction of what exists. 5%. That is how much of the universe is made of ordinary matter. The atoms that make up stars, planets, gas clouds, and you, only 5%. The other 95% is something else entirely, something we cannot see, something we cannot touch, something we can only detect through its gravitational effects, and that something is divided into two mysterious components that dominate the universe in ways we are only beginning to understand. 27% of the universe, stark matter. 68% is dark energy, and neither one makes any sense according to what we thought we knew about physics. Let me start with dark matter, because at least we can observe its effects directly. In the 1930s, an astronomer named Fritz Zwicky was studying the Coma Cluster, a collection of over 1,000 galaxies, about 320 million light years from Earth. He measured how fast the galaxies were moving within the cluster, and he noticed something strange. The galaxies were moving too fast. According to his calculations based on the visible mass in the cluster, the galaxies should be moving much slower. At their observed speeds, they should fly apart. The cluster should not hold together. But it does. It has been stable for billions of years. Zwicky concluded that there must be additional mass in the cluster, mass that we cannot see, mass that only interacts through gravity. He called it dark matter, though at the time most astronomers dismissed the idea. But in the 1970s, astronomer Vera Rubin made observations that confirmed Zwicky's suspicions. She studied the rotation curves of galaxies. Specifically, she measured how fast stars orbit around galactic centers at different distances. According to Newton's laws, stars farther from the galactic center should orbit more slowly, just like planets farther from the sun orbit more slowly. But that is not what Rubin found. Stars at the outer edges of galaxies orbit just as fast as stars closer to the center. The rotation curves are flat, not declining. This should not be possible unless there is additional mass that we cannot see. Mass distributed throughout the galaxy in a large halo, extending far beyond the visible disk. That invisible mass provides the extra gravity needed to keep the outer stars moving at high speeds. Multiple lines of evidence now confirm the existence of dark matter. Gravitational lensing shows us how light bends around massive objects. When we observe distant galaxies whose light is bent by foreground galaxy clusters, we can map where the mass is, and the mass does not line up with the visible galaxies. There is far more mass than we can see, distributed in huge halos around and between the visible structures. The cosmic microwave background, which we will talk about soon, shows tiny temperature fluctuations that reveal how matter was distributed in the early universe. Those patterns only make sense if dark matter existed back then, providing the gravitational scaffolding for ordinary matter to clump around. Computer simulations of galaxy formation cannot reproduce the structures we observe unless dark matter is included. When scientists add dark matter to their models, galaxies form naturally. Without it, the simulations fail. Everything tells us dark matter is real, but we have no idea what it is. It is not made of atoms. If it were, we would be able to detect it through electromagnetic radiation. It would emit or absorb light, even if very faintly, but dark matter does not interact with light at all. It is completely invisible across the entire electromagnetic spectrum. It is not black holes or other compact objects made of ordinary matter. We can detect those through gravitational effects and other means. Dark matter is something else. The leading theory is that dark matter consists of exotic particles that do not interact electromagnetically, particles that only feel gravity, and possibly the weak nuclear force. Scientists call these hypothetical particles WIMPs, which stands for weakly interacting massive particles. But despite decades of searching, we have not detected a single WIMP. Underground detectors wait for dark matter particles to collide with atomic nuclei. Particle accelerators try to create dark matter in high-energy collisions. Telescopes search for indirect signs of dark matter annihilation, but so far, nothing definitive. Dark matter is everywhere. It passes through you constantly. Billions of dark matter particles stream through your body every second, never interacting, never slowing down, completely oblivious to the ordinary matter they pass through. You are transparent to dark matter. It sees straight through you as if you were not there. And yet, dark matter is the reason galaxies exist, the reason galaxy clusters hold together, the reason large-scale structures formed in the universe. Without dark matter, the universe would be completely different. Stars might still form, but galaxies would not. There would be no spiral arms, no galactic clusters, no filamentary structures connecting galaxy superclusters. Dark matter built the framework of the cosmos. It provided the gravitational wells into which ordinary matter fell, creating the structures we see today. In a sense, we live in a universe shaped by something invisible, something we cannot even detect directly, yet something absolutely essential to our existence. But if dark matter is mysterious, dark energy is even stranger. In 1998, two independent teams of astronomers were studying distant supernovae, using them as standard candles to measure cosmic distances. They expected to find that the expansion of the universe was slowing down. Gravity from all the matter in the universe should pull back against the expansion, gradually decelerating it over billions of years. But that is not what they found. The expansion was not slowing, it was accelerating. The universe is expanding faster now than it was billions of years ago, and that makes no sense. Acceleration requires energy. Something must be pushing the universe apart, overpowering gravity, and whatever that something is, it fills all of space uniformly. We call it dark energy, though that name tells us nothing about what it actually is. Dark energy makes up 68% of the total energy content of the universe. It is the dominant component, and we have no idea what causes it. One possibility is that dark energy is the cosmological constant, a property of space itself. Einstein originally proposed this idea in 1917, then rejected it, but modern observations suggest he might have been right after all. Empty space might have an intrinsic energy density, a small amount of energy associated with every cubic centimeter of vacuum. That energy would remain constant even as the universe expands. As space stretches, more space is created, bringing more dark energy into existence. The effect compounds over time, causing the expansion to accelerate. If this is correct, dark energy is not a substance or a field, it is a fundamental property of space itself. Asking what dark energy is made of would be like asking what emptiness is made of. It just is. Another possibility is that dark energy is a dynamic field, something called quintessence. Unlike the cosmological constant, which remains constant over time, quintessence could vary. Its strength might change as the universe evolves. This would explain why dark energy seems to have become dominant only recently in cosmic history rather than overwhelming matter and dark matter from the beginning. But we do not know which explanation is correct. We do not even know if either explanation is correct. Dark energy might be something completely different, something beyond our current understanding of physics. What we do know is that dark energy is causing the universe to expand faster and faster. Galaxies that are not gravitationally bound to us are moving away at ever increasing speeds. Eventually, they will recede faster than light can travel through expanding space, crossing the cosmic event horizon and disappearing from view forever. In a few 100 billion years, all galaxies outside our local group will be gone, carried away by the accelerating expansion. The observable universe will shrink. Future astronomers, if they exist, will look at the sky and see only their own galaxy, with no evidence that other galaxies ever existed. They will not be able to discover what we know about the universe's expansion or its origin. The evidence will have disappeared beyond the horizon. Dark energy is not just accelerating the expansion, It is erasing the universe's history, hiding the evidence of the Big Bang, making the cosmos unknowable to future observers. And we can do nothing about it. No force can stop dark energy. No technology can reverse the expansion. The universe will continue accelerating, continue pushing galaxies apart, until eventually the expansion becomes so extreme that even gravitationally bound structures like galaxy clusters might be torn apart. This hypothetical end is called the Big Rip. If dark energy continues to strengthen over time, it could eventually overcome all forces holding matter together. First, galaxy clusters would dissolve, then galaxies, then solar systems, then planets, then molecules, then atoms. Everything would be ripped apart by the accelerating expansion of space itself. But we do not know if the Big Rip will happen. It depends on the exact nature of dark energy. If dark energy is the cosmological constant, the Big Rip will not occur. The expansion will accelerate, but not to the point of tearing apart bound structures. If dark energy is quintessence and gets stronger over time, then the Big Rip becomes possible. For now, dark energy is stable. It has been accelerating the expansion for about 6 billion years, roughly the time since the Sun formed, and it will continue doing so for billions more years. The effects are slow, gradual. Nothing dramatic will happen in the near future, but the implications are profound. The universe we inhabit is dominated by two components we cannot see, cannot touch, cannot understand. Dark matter shapes the structure of galaxies. Dark energy controls the ultimate fate of the cosmos, and together they make up 95% of everything that exists. We are made of the 5%, the rare stuff, the minority component, the visible matter that emits and absorbs light, forms atoms, creates chemistry, enables life. Everything we have ever known, every person who has ever lived, every civilization that has ever existed, all of it built from the 5%. The other 95% is invisible to us. We can infer its existence. We can measure its effects, but we cannot directly observe it. We cannot study it in laboratories. We cannot hold it or manipulate it. We can only watch as it shapes the universe around us. And that is humbling. That is a reminder that despite all our knowledge, despite centuries of scientific progress, we still do not understand the fundamental nature of reality. The universe is stranger than we imagined, stranger than we might be capable of imagining. Dark matter and dark energy are not minor mysteries. They are the dominant components of existence, and we have barely scratched the surface of understanding them. Perhaps future generations will solve these mysteries. Perhaps they will discover what dark matter particles are and detect them directly. Perhaps they will understand the nature of dark energy and whether it will lead to a big rip or some other fate. Or perhaps these mysteries will persist. Perhaps dark matter and dark energy are fundamentally unknowable, beyond the reach of our instruments and our theories. Perhaps the universe will always keep some secrets, always remain partly hidden, always remind us that we are small and our knowledge is limited. But even not knowing, we can appreciate the mystery. We can marvel at a universe composed mostly of invisible things. We can look at the galaxies spinning in the night sky and remember that they are held together by something we cannot see. We can watch the universe expand and know that something we do not understand is pushing it apart. The visible universe is beautiful, but the invisible universe, the dark universe, the 95% we cannot see, that is perhaps even more beautiful because it remains unknown, mysterious, waiting for discovery, or perhaps forever beyond our reach. Tonight, as you drift toward sleep, dark matter particles pass through your body by the billions. Dark energy pushes the fabric of space apart, slowly, inexorably, carrying distant galaxies beyond the horizon. Both processes invisible, both essential, both reminders that the universe is larger and stranger than our senses can reveal. We live in a cosmos made mostly of darkness, not the darkness of evil or absence, but the darkness of mystery, the darkness of the unknown, and in that darkness, perhaps, lies the most profound truth of all, that we will never know everything, that the universe will always surprise us, that wonder is not just a feeling, but a fundamental condition of being conscious in a cosmos we do not fully understand. Rest now in the dark universe. Tomorrow it will still be mostly invisible, still mostly mysterious, still composed of things we cannot see, but know must be there, holding everything together, pushing everything apart, shaping reality in ways we are only beginning to comprehend. There is light all around you right now that you cannot see. Ancient light, the oldest light in the universe, light that has been traveling through space for 13.8 billion years, carrying information from a time before stars existed, before galaxies formed, before anything resembled the universe we know today. This light is everywhere. It fills every cubic centimeter of space. It passes through you constantly. And if you had eyes that could see microwave radiation instead of visible light, the entire sky would glow with it, uniformly, in every direction. A faint, nearly perfect backdrop of ancient photons that tell the story of the universe's birth. This is the cosmic microwave background, the CMB, and it is one of the most important discoveries in the history of science. The story begins in 1964. Two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Labs in New Jersey, trying to calibrate a sensitive antenna for satellite communications. But they kept detecting an annoying background noise. No matter where they pointed the antenna, no matter what time of day or night, the noise was always there. A faint hiss at microwave wavelengths, about 7 centimeters. At first, they thought it was interference from New York City. Then they thought it might be radiation from nuclear tests. They even suspected it might be caused by pigeon droppings inside the antenna. They cleaned out the antenna thoroughly, removed all the droppings, but the noise remained. Finally, they learned about a prediction made by physicists Ralph Alpher and Robert Herman in 1948. Alpher and Herman had been working on Big Bang theory, trying to understand how the universe evolved from a hot, dense state. They calculated that if the universe began in a Big Bang, there should be leftover radiation from that event, cooled by the expansion of space to a temperature of about 5 Kelvin. Penzias and Wilson measured the temperature of their background noise, about 3 Kelvin. Close enough. They had accidentally discovered the cosmic microwave background, the remnant radiation from the Big Bang itself. Let me explain what the CMB actually is and why it exists. In the beginning, the universe was incredibly hot and dense, far too hot for atoms to form. Matter existed as a plasma of free protons, electrons, and photons. The photons were constantly scattering off the free electrons. Light could not travel far. The universe was opaque, like being inside a thick fog where you cannot see more than a few feet in any direction. But as the universe expanded, it cooled. After about 380,000 years, the temperature dropped to around 3000 Kelvin. At that temperature, protons and electrons combine to form neutral hydrogen atoms. This event is called recombination, even though the protons and electrons were not recombining, but combining for the first time. Once atoms formed, photons stopped scattering constantly. Light could suddenly travel freely through space. The universe became transparent, and all those photons that had been trapped in the hot plasma were released, streaming in every direction. Those photons have been traveling ever since. For 13.8 billion years, they have crossed the expanding universe. And as space expanded, the wavelengths of those photons stretched. What started as visible light, orange and red, shifted into the infrared, then into microwaves. Today, those photons have a wavelength of about 1 to 2 millimeters, corresponding to a temperature of 2.725 Kelvin. That is the cosmic microwave background. The light from the moment the universe became transparent, redshifted by 13.8 billion years of expansion, now arriving at Earth as faint microwave radiation coming from every direction in the sky. When you map the CMB, you are seeing the universe as it was 380,000 years after the Big Bang. You are seeing the baby picture of the cosmos, the oldest light we can possibly detect. Nothing older can reach us because before recombination, the universe was opaque. The CMB is the earliest snapshot we have. That snapshot is remarkably uniform. If you measure the temperature of the CMB in one part of the sky, you get 2.725 Kelvin. If you measure it in another part of the sky, you get 2.725 Kelvin. The temperature is the same everywhere, to within about 1 part in 100,000. This uniformity is both expected and surprising. Expected because the early universe was almost perfectly smooth, with only tiny density variations. Surprising because regions on opposite sides of the sky are so far apart that light could not have traveled between them in the 380,000 years since the Big Bang. They should not have the same temperature. They should not be in thermal equilibrium, yet they are. This is called the horizon problem, and it is one of the reasons physicists proposed cosmic inflation. If the universe underwent a brief period of exponential expansion in its first fraction of a second, then all the regions we see were once close together in thermal equilibrium. Inflation stretched them apart, but they retained their similar properties. But the CMB is not perfectly uniform. If you measure very carefully, you find tiny temperature fluctuations, regions that are slightly hotter or slightly colder than average. These fluctuations are about 0.00001 Kelvin, just 1 part in 100,000, but they are incredibly important. Those tiny fluctuations represent density variations in the early universe, regions that were slightly denser than average, and those denser regions had slightly stronger gravity, pulling in more matter. Over millions and billions of years, those tiny fluctuations grew into the galaxies, galaxy clusters, and large-scale structures we see today. The pattern of fluctuations in the CMB tells us about the composition of the universe. How much ordinary matter, how much dark matter, how much dark energy. The shape of the fluctuations depends on these quantities. By measuring the CMB precisely, we can determine the fundamental parameters of the universe. And that is exactly what multiple space missions have done. The COBE satellite in 1992 first detected the fluctuations. The WMAP satellite from 2001 to 2010 mapped them in detail. The Planck satellite from 2009 to 2013 measured them with exquisite precision. From those measurements, we know the universe is 13.8 billion years old. We know it is spatially flat, meaning parallel lines stay parallel even across cosmic distances. We know it is made of 5% ordinary matter, 27% dark matter, and 68% dark energy. All of this from studying tiny temperature variations in ancient light. The CMB also tells us something profound about our place in the universe. When you look at the CMB, you are looking at the edge of the observable universe, not because there is nothing beyond, but because light from farther away has not had time to reach us yet. The CMB is the most distant thing we can see because it is the oldest light that exists. Everything we observe, every galaxy, every star, every structure, all of it is contained within the sphere defined by the CMB. That sphere has a radius of about 46 billion light years, not 13.8 billion light years, because space has been expanding while the light was traveling. The observable universe is larger than you might think. But beyond that sphere, there is more universe, probably infinitely more. Regions we cannot see because their light has not reached us. Regions that are receding so fast that their light will never reach us. The universe beyond the CMB is unknowable to us, hidden behind a horizon of ancient light. And that horizon is not static. As time passes, light from more distant regions reaches us. The observable universe grows, but at the same time, accelerating expansion caused by dark energy is pushing distant galaxies beyond the cosmic event horizon, where they will disappear from view. The observable universe is both growing and shrinking, depending on which effect dominates. Right now, we live in an era when the CMB is visible, when we can see the baby picture of the universe, when the evidence of the Big Bang is written in the sky in microwave radiation. But this era will not last forever. In the far future, trillions of years from now, the universe will have expanded so much that the CMB will be redshifted beyond detection. The temperature will drop from 2.725 Kelvin to nearly absolute zero. The photons will have wavelengths measured in meters, then kilometers, then longer. Eventually, the CMB will fade into undetectability. Future civilizations, if any exist, will not be able to see the CMB. They will not have direct evidence of the Big Bang. They will have to infer the universe's origin from other clues, from the abundances of light elements, from the recession of galaxies. But the clearest evidence, the light from the beginning, will be gone. We are lucky to live when we do, when the universe is old enough for stars and planets and life to exist, but young enough that the CMB is still detectable. We exist in a brief window of cosmic history when the universe is knowable. The CMB is also a reminder of how far we have come. For most of human history, we did not know the universe had a beginning. We did not know it was expanding. We did not know about the Big Bang. All of that knowledge has come in the last century, and the key evidence came from detecting faint microwave radiation that permeates all of space. Radiation that was always there, always passing through us, but invisible until we built the right instruments to detect it. The universe was telling us its story the entire time. We just needed to learn how to listen. Tonight, as you lie in your bed, billions of CMB photons pass through you. They entered your room through the walls, which are transparent to microwaves. They pass through your body, which is also transparent to these wavelengths. They exit through the floor and continue their journey, 13.8 billion years old and still traveling. Each photon carries a tiny piece of information about the early universe, about the temperature at recombination, about the density fluctuations that became galaxies, about the geometry of space. And all of that information is encoded in the photon's energy, its direction, its polarization. You are immersed in ancient light, light that began its journey when the universe was 380,000 years old. Light that has traveled across billions of light years of expanding space to arrive at this moment, at this place, at you. And it does not care whether you notice it. It just keeps going, carrying its message, available to anyone who knows how to read it. The cosmic microwave background is the universe's memory. It remembers the Big Bang. It remembers the moment when light first traveled freely. It remembers the tiny fluctuations that became everything we see today. And it shares that memory with anyone who looks, with any civilization that develops the technology to detect it. We are not special for discovering the CMB. Any technological civilization would eventually find it. It is there, obvious and unavoidable once you know where to look. We just happen to be the civilization that looked first on this particular planet, in this particular galaxy. And what we found is humbling. The universe had a beginning. It was once unimaginably hot and dense. It expanded and cooled. It became transparent. And now, 13.8 billion years later, we can still see the light from that moment, filling the sky, telling us where we came from. The CMB is proof that the universe is not eternal and unchanging. It is evolving. It has a history, and we are part of that history, conscious beings made of atoms that were forged in stars, standing on a planet that formed from a disk of gas and dust, looking up at the sky and seeing the echo of creation itself. That is what the cosmic microwave background represents. Not just radiation, not just data, but evidence of our origin, proof that everything began somewhere, sometime, and has been unfolding ever since, according to physical laws we can understand. Rest now surrounded by ancient light. Tomorrow it will still be there, still traveling, still carrying the story of the universe's birth. The cosmos remembers where it came from, and for a brief moment in its history, we remember too. We have journeyed together through time and space tonight, from the light of distant stars to the atoms in your body, from the rotation of planets to the expansion of the universe itself. We have seen beauty and mystery, violence and tranquility, birth and death across cosmic scales. And now, as our journey comes to an end, I want to tell you about the future, the long, patient, inevitable future that awaits the universe. Everything ends. We know this instinctively. Stars die, planets cool, even galaxies eventually exhaust their fuel. But the universe does not end quickly. It does not end dramatically. It ends the way it has done everything else, slowly, patiently, taking its time. Right now, we live in what astronomers call the stelliferous era, the age of stars, the period when the universe contains vast numbers of actively fusing stars, creating light and heat, and the heavy elements necessary for planets and life. This era began a few 100 million years after the Big Bang, when the first stars ignited, and it will continue for trillions of years into the future. But even the stelliferous era will end. Stars form from gas clouds and galaxies, but galaxies have a finite amount of gas. Some gets locked up in stars, some gets blown out of the galaxy by stellar winds and supernovae. Some falls into black holes, and as time passes, less and less gas remains available for star formation. Currently, the Milky Way forms about one or two new stars per year. That might sound slow, but there are hundreds of billions of stars already shining. The galaxy is vibrant, active, full of stellar nurseries where new suns are being born. But in a few billion years, star formation will slow, the rate will drop to less than one star per year, then one star per century. The gas will run out, the stellar nurseries will go quiet, and eventually no new stars will form at all. Astronomers estimate this will happen in about 100 trillion years. 100 million years. That is more than 7,000 times longer than the current age of the universe. It is an incomprehensibly vast span of time, but eventually it will arrive. And when it does, the universe will enter a new phase, the degenerate era, the age when the only stars remaining are the longest lived ones, small red dwarfs, burning their hydrogen so slowly that a single star can shine for trillions of years. White dwarfs, the dead cores of sun-like stars, glowing faintly from leftover heat, but no longer fusing anything. These remnant stars will provide the last light in the universe. Scattered throughout dark galaxies, they will glow like dying embers in a fireplace, growing dimmer with each passing eon. The smallest red dwarfs, stars with only about 8% of the sun's mass, can last for 10 trillion years or more. They burn hydrogen so efficiently, mixing their entire mass through convection, that they use every available atom of fuel. But even these miserly stars will eventually exhaust their hydrogen and cool into white dwarfs. By 100 trillion years, essentially all star formation will have ceased. By 120 trillion years, even the longest lived red dwarfs will have burned out. The last natural light in the universe will fade. Galaxies will go dark. Not all at once, not dramatically, just slowly, star by star, until finally the last one dims and goes out. And then there will be no more natural starlight anywhere. The universe will enter true darkness. But darkness does not mean emptiness. Dead stars still exist. White dwarfs, neutron stars, black holes, brown dwarfs that never ignited fusion, planets orbiting dead suns. All of this material remains, held together by gravity, still orbiting, still existing, just not shining. This is the black hole era, the age when black holes are the dominant stellar remnants. Most stars will have ended as white dwarfs or neutron stars, but the most massive stars collapsed into black holes. And black holes, unlike other stellar corpses, do not just sit there forever. Stephen Hawking discovered that black holes emit radiation. Hawking radiation, he called it. It comes from quantum effects near the event horizon. Virtual particle pairs form near the horizon, and occasionally one particle escapes while the other falls in. To an outside observer, this looks like the black hole is radiating energy. The process is incredibly slow. A black hole with the mass of the Sun would take 10 to the 67th power years to evaporate completely. That is 10, followed by 67 zeros, longer than the current age of the universe, raised to the fifth power, almost unimaginably long. But given enough time, even black holes evaporate. The smaller ones go first. Black holes with only a few times the sun's mass will evaporate in 10 to the 70th years or so. Larger black holes take longer. Supermassive black holes, the ones at the centers of galaxies with millions or billions of solar masses, will take 10 to the 100th years to evaporate. And so the universe will wait, patiently, silently, as black holes slowly radiate away their mass, photon by photon, over timescales that make 13.8 billion years seem like an eye blink. Eventually, after inconceivable spans of time, the last black hole will evaporate. The last massive object will dissolve into radiation, and the universe will enter its final phase, the dark era. In the dark era, all that remains is a thin soup of photons, neutrinos, and a few remaining elementary particles. No stars, no planets, no black holes, just radiation spread across an exponentially expanding universe, cooling asymptotically toward absolute zero. The temperature of empty space will be measured in billionths of a Kelvin, then trillions, then quadrillions, approaching zero but never quite reaching it. The universe will become cold and dark and empty in a way that is difficult to comprehend. This is called heat death, maximum entropy, the state where no useful energy remains, where no work can be done, where nothing interesting can happen because there are no energy gradients to drive change. In this state, the universe will simply exist, unchanging, timeless in a sense, because without events to mark time's passage, time itself becomes meaningless. The universe will have reached thermal equilibrium, the state it has been approaching since the Big Bang, and there it will remain forever, or at least as close to forever as makes no difference. But here is something remarkable. Even this heat death is not the end of complexity. Not quite. Quantum mechanics allows for random fluctuations, even in a universe at maximum entropy. Occasionally, particles will spontaneously assemble into more ordered configurations. Given infinite time, every possible configuration of matter will eventually occur by chance. These are called Boltzmann brains. The idea is that in an infinite universe, with infinite time, random fluctuations could briefly create structures as complex as a human brain, complete with false memories of a life that never existed. The brain would exist for a moment, then dissipate back into the void. This is a strange and unsettling idea, but it illustrates that even in heat death, given enough time, the universe can surprise you. Quantum fluctuations ensure that nothing is truly static. Change, however rare and random, continues forever. But all of this, the entire future I have described, takes place over time scales so vast that they lose all meaning. The stelliferous era, when stars shine, lasts 100 trillion years. The degenerate era lasts another few trillion. The black hole era lasts 10 to the 100th years. And the dark era lasts forever. Compared to these timescales, human civilization is a spark, a brief flicker of consciousness in the cosmic night. We have existed for perhaps 200,000 years as a species. Recorded history covers maybe 5,000 years, and all of it is contained within the first 13.8 billion years of a universe that will continue for trillions upon trillions of years more. We live in the universe's youth, in its vibrant phase, when stars are abundant, and galaxies are bright, and planets orbit in the warm glow of active suns. We are witnessing the universe at its peak, and we should appreciate that, because in the far future, observers, if any exist, will look at a much darker cosmos, fewer stars, colder galaxies, less structure, and eventually no stars at all, just the fading remnants of a universe that once shone with the light of 100 billion trillion suns. But in that future is unimaginably far away. For now, tonight, as you lie in your bed, the universe is still young, stars are still forming, galaxies are still bright, planets are still warm, life is still possible. And that is a gift, a brief window in cosmic history when matter organized itself into something as complex and wonderful as a conscious being, when atoms that were forged in stellar cores came together to form you, allowing the universe to see itself, think about itself, wonder about itself. The future is long and patient, and ultimately dark, but we do not live in the future. We live now in the bright era, in the age when understanding is possible, when wonder is abundant, when the night sky is full of stars to contemplate and galaxies to study and mysteries to unravel. So tonight, as you drift toward sleep, let go of worries about the distant future. Let go of anxiety about tomorrow or next week or next year. Those timescales are infinitesimal compared to the cosmic timescales we have discussed. Your problems, real as they feel, are temporary, brief flickers in a much larger story. The universe will continue long after you are gone. Stars will shine, planets will orbit, galaxies will rotate, and eventually, trillions of years from now, it will all fade away. But that ending is so far away, so impossibly distant, that it might as well not exist. What exists is now, this moment. You lying in your bed, conscious and aware, a temporary pattern of atoms arranged by 4 billion years of evolution into something that can think and feel and appreciate the cosmos. You are the universe experiencing itself. For a brief moment, matter became aware, and that moment is precious because it is rare. Most matter never experiences awareness. Most atoms never participate in consciousness, but you do right now. Then, or when you wake up tomorrow, the stars will still be shining, the sun will still be burning, Earth will still be spinning, the universe will still be here, patient and eternal, on timescales that dwarf human concerns. You have nothing to worry about tonight. The cosmos has time, infinite, patient time, and for now, for this brief moment, you are part of it. You are stardust that learned to think, atoms that came together to wonder about atoms. Rest now. The universe will take care of itself. It has been doing so for 13.8 billion years. It will continue doing so for trillions more. And you, briefly, wonderfully, impossibly, are here to witness a tiny fraction of that infinite story. The journey is over. The stars will guide you into dreams, and tomorrow, when you wake, the universe will still be here, still expanding, still evolving, still creating moments of beauty and wonder for anyone who takes the time to look. Sleep peacefully under ancient starlight. The cosmos has been waiting billions of years for you to exist. And now that you are here, it asks nothing of you except perhaps a moment of appreciation, a brief recognition that you are part of something vast and beautiful and endlessly patient. Good night. The universe will still be here tomorrow, and so will you, both of you continuing your journeys through space and time, together yet separate, connected by the same atoms, the same physics, the same fundamental forces that have been shaping reality since the beginning. The stars are waiting, the night is deep, and sleep comes gently to those who understand their place in the cosmic story. Rest now. The universe has time, and so do you.